Okay, so welcome to this tutorial. The problem that we want you to kind of talk to you about is if we take planning and take it into the real world, then we have to deal with the uncertainty of the world, right? Because otherwise, if we use generative planning techniques, right, they can be more robust, but they also can be dangerous, right? And so often the barrier to adoption is the fact that you have generative techniques which didn't know about both the uncertainty of the world and didn't reason about it. There's a lot of work on probabilistic planning which will deal with that. But then the other one is that the algorithms not only need to know about uncertainty, but they need to know about what is considered to be acceptable risk, right? So kind of the fundamental notions that we'll explore is that when you specify desired behavior in an uncertain world, you need to specify what level of risk that you're willing to accept with respect to certain safety constraints. And then the algorithms that you're designing need to be able to guarantee you operate within those risk bounds, okay? So what we'll do during the first half hour is to introduce, kind of motivate the notion of planning on uncertainty and risk, and what it talks about is to map into the real world. We'll then introduce a particular kind of generative temporal planning framework where we're dealing with both the discrete and continuous world. And then we'll talk about two different families of algorithms which allow you to deal with risk in that context. And the two different families that we'll be dealing with is, first is that we need to deal with the fact that although we want to plan in a discrete world, the world is in fact continuous. So we do need to map from the discrete to the continuous world. And that's usually a problem of motion planning or trajectory optimization. So the first thing we want to talk about is how do you go from a discrete world to a continuous world by performing trajectory optimization to implement your plan. And then what we'll do is we'll fold in uncertainty and risk within trajectory optimization. That's not something that you normally see in the ICAPS community, but to apply these things, you really need to be able to understand trajectory optimization. The good news is just constraint programming at one level, right? So it's not something that's kind of foreign to us. The second thing that you want to deal with is to deal with uncertainty at a more strategic level, where you're dealing with more of the, for example, the temporal activity planning, right? But what is important is that you have coordination and temporal constraints, so we need to deal with uncertainty in time. So the second half of the tutorial, right, which is what Erez will be presenting, is to how do we go from temporal problems, such as simple temporal problems or disjunctive temporal problems, and introduce a probabilistic notion of uncertainty. This community is focused a lot on representation of uncertainty, where you have an interval over the uncontrollable variables, and you say, well, given that it could take anywhere between 15 minutes to 2 hours to get the projection system to work, do I have a schedule that will work correctly, right? Often the world will have unbounded uncertainty, right, in which case you can't put an exact set bound. So in those cases, you want to use more of a probabilistic approach to represent the uncertainty, and then you want to take in the fact that there's some risk of failure, right, and you don't want to be so conservative, right, that you guarantee to achieve everything, but there is some probability of success that you want to achieve. Okay, and so that'll be the second part, and that should be probably the more comfortable part for those who kind of know about temporal problems. We decided to start with trajectory optimization, though it's less familiar, just to try to expose you to something more new. And then we'll take those ideas and carry the ideas to temporal problems as well. Now, the underlying concept that we'll talk about is that if somebody tells you how much risk that you're willing to accept, then the problem isn't to minimize risk. It's to try to do the best job or achieve the highest utility within that risk bound, right? So if we end up saying, I'm willing to accept a 1% risk of missing my flight, then you may say, okay, I'll arrive an hour ahead of time. And your task isn't to arrive 3 days beforehand to minimize risk. Yours is to try to say, well, can I make sure that I did my shopping, I did my packing, I went to the grocery store, but I'm still working within those risk bounds, okay? So we think of risk as something that's been given to us as a resource. It's precious, so we want to use it very carefully. So what we'll do is we'll try to figure out where do we want to express risk. So from an approximate standpoint, it's quite nice because it allows us to say it's okay to approximate, right? And you can approximate as much as you want to, and you can make the inference problem simpler by not considering options. But you need to do that in a way which operates within your risk bound, right? And so what you want to do is when you use the risk, you want to use it when it helps you the most, okay? So the central theme throughout this tutorial will be the notion of risk allocation, okay? Now, I will want to try to expose you to some of the other kind of approaches to dealing with stochastic problems. These are instances of stochastic optimization problems, but then I'll kind of focus in on risk allocation. Okay, so the world is uncertain, right? And bad things happen. Bad things happen that we consider to be unacceptable, right? And so David at NASA would kind of agree that when NASA talks about trying to design a system, typically one will talk about a requirement, which is that the probability of failure was in some rate. So, for example, in a deep space mission, right, there will be a requirement in terms of the probability of completing the first phase of the mission has to have some probability. When you come up with a landing site, there's a landing ellipse. You have to be able to say that the probability of landing within that ellipse is within some interval, within some risk bound. Okay, so typically we consider to say that we're not going to take arbitrary amounts of risk for arbitrary amounts of reward. There is a hard constraint that we consider to be acceptable or not. Okay, now when we talk about uncertainty, often the uncertainty impacts the dynamics. So suppose, for example, we talk about a weather system, right? So a weather system causes the wind speed to be uncertain. If we were interested in energy problems, then that creates uncertainty, for example, in wind power, right, which makes the grid more destabilized, which means that there's some likelihood that supply doesn't meet demand. So we have to be able to figure out how much, for example, how much wind generation, how much solar arrays we provide, right? So we have enough capacity, right, to meet demand, but we can't do that with absolute uncertainty, right? So we have to take some level of risk. Okay. If we talk about autonomous vehicles, on the other hand, then in air vehicles or underwater vehicles, right, the uncertainty can significantly impact the vehicle position, and that could cause the vehicle to collide, especially when we're dealing with underwater context. So we have to deal with that uncertainty as well. Okay, so we have to deal with that uncertainty. Second, we have to deal with the fact that the uncertainty is impacting the continuous state variables, not the discrete. So we need to be able to reason about the continuous variables, not just the discrete state. And then often this uncertainty isn't bounded to some finite interval, right? It is usually some probability distribution, such as a Gaussian, where the uncertainty is infinite at one level. Okay, so I'm just going to kind of go back and kind of play up on these two examples, right? So one is energy, and then the other one is vehicles. So I'll use those two examples. Erez and I will throughout the tutorial. So here's one example where we're applying the risk allocation techniques I'll talk to you about. It's a solar home. It's a passive solar home, right, where you have solar radiation coming in. You can adjust these windows by making them opaque or clear, opening or closing them. And so what you want to do is to maximize your use of solar radiation, right? And then you want to use conventional heating to kind of back up as appropriately, right? Or air conditioning. The uncertainty is cloud cover, and because of cloud cover, that will affect solar radiation. Okay, so you have a series of uncertainties in terms of the supply. You also have some uncertainty in terms of the demand as well, which is you don't know exactly when the occupant will arrive or not. But since the system has a lot of inertia, it will take time to heat up or cool off. Right? You can't just wait till they arrive and then adjust the temperature, right? You have to have some expectation of when they're likely to arrive or not. Okay, so that's kind of a nice example where there's both uncertainty in the goals that you're trying to achieve, which is helping the occupant, and then uncertainty in the resources being provided to achieve those goals. Okay, a second one is the example of environmental observing systems. So we spent a fair amount of work on underwater systems. The vision in underwater systems is if we can have a network of autonomous underwater vehicles, right, then we can avoid using these kind of expensive ships, right, which are deploying a very small set of sensors. And instead, we can have a very large network of very cheap underwater vehicles, which are doing a much better and affordable job of observing the ocean. The challenge in this case is that to operate a bunch of these vehicles, then you really don't want to have to hand code them at a low level. You want to use automated planning techniques to control these vehicles, but they're dealing with an uncertain environment, and a lot of the more cheap, affordable vehicles are much more susceptible to disturbances in the environment due to currents. So I'll point to one example that we did back at MBARI on a sabbatical I had in 2008, and then I'll give another example from 2 months ago that we did in the East Timor Sea. This is an example where we're taking an underwater vehicle. We're trying to map Monterey Bay, right? And so what you want is you want the vehicle to be as close to the seafloor as possible to get a better resolution image. But since this is what Monterey Bay looks like, right, then the danger is the closer you get to the seafloor, then the greater likelihood that the vehicle would be pushed into colliding. So what you have to do is you have to balance the risk, right, of colliding the seafloor against the utility, right, and improved imaging. So if you frame this as a deterministic optimization problem, which is what they would classically do, and you specify a a distance from the seafloor, right, and say you want to follow that distance, if you solve that as an optimization, then what's shown in green is a heuristic technique that they ended up using, right? Here's an encoding of it as a mixed integer linear program, as a deterministic optimization, and what you see is that the expected utility would be high, right? It stays kind of exactly where you like it, but there's these spikes here, and so each of these spikes incurs a very significant risk of losing the vehicle. So the problem here is that when we want to optimize these systems, it's a constraint optimization problem. A constraint optimization problem will usually find the optimal solution at a constrained boundary, and that makes the solution quite brittle, right? So somehow you have to be able to tell the algorithm that I want to stay some distance from those constraints to be able to deal with uncertainty, and you can either do that by providing some offset, right, or some safety zone, right, or some set bound, or you need a probabilistic approach to dealing with that. Okay, so that's why you don't really want to use deterministic algorithms to find the optimal solutions. You need to be able to handle the uncertainty. So stochastic optimization says, well, we have an explicit set of random variables. We'll describe a distribution of those random variables, such as the currents, and then associated with your hard constraints, such as not colliding to the seafloor, you introduce a chance constraint, which is simply the probability that that constraint can be violated. Okay, so in this case, we can say that the probability that we'll collide into the seafloor is 1% or 5% or 0.001%, and based on that, then you can frame it as a stochastic optimization problem, and then you can come up with a solution which operates within that risk bounds while maximizing science utility. So that's the notion, right? So we can frame these problems very easily as stochastic optimization problems. The challenge is solving those problems, and those algorithms tend not to scale very well. And I'll talk about why stochastic optimization tends to be a hard problem. Okay, so that's kind of two motivating examples. If you talk about air vehicles, then the same issues will occur as well. So when you then talk about dealing with uncertainty, then there's a number of approaches in terms of dealing with uncertainty. And they have to deal with how do you fold uncertainty either in the utility function or the constraints. So the one that's probably most familiar within the AI and the MDP community is that what you want to do is to maximize expected utility. Okay, so what you do is you take some utility, such as science gain. You also take the probability of failure, and you talk about the loss, right, or the cost of failure, and then you just add that as a penalty function in your objective. But then the issue there is what's the utility of losing a $3 billion spacecraft, or when you talk about kind of air flight or human space exploration, then you talk about the utility of dying. So usually you don't talk about that as there's unbounded, you're willing to accept unbounded probability of failure for arbitrary utility. You wouldn't really want to specify a bound. Another thing you can do is to minimize risk, right? And a number of approaches within the community explore minimizing risk. But the best way to minimize risk if you're ignoring utility is simply not to ever leave your room. And some people have decided to do that in their lives, but it's not such a successful strategy. So the one that we're advocating is that you do want to be able to put the uncertainty both in the utility, but also within the hard constraint. So you do want to be able to express a constraint which says the probability of failure of a particular subset of activities at a maximum can be within this bound. Now, it's also the case that you can still put a trade-off between failure and utility within the objective function. There's no reason why you can't do both of this. So this isn't saying it's an either or, but it's saying that there are cases where you want to be able to put an absolute bound on the probability of failure, and how do you deal with that? And then there are other ones, right? So you can minimize risk to achieve, for example, utility bound, which is really the dual of this, right? So what you do is you say, here's my target utility. I want you to hit that target and then try to minimize risk within that target. But it's much harder to be able to kind of come up as a modeler a priori to know what is a reasonable utility bound. It's really a trade-off between the two. Okay, so what we would then focus on is this notion of maximizing expected utility subject to a bound on risk, and we'll talk about within our decision-making and optimization algorithms, how do we deal with bounded risk. We then have to talk about, so of the family of problems you can solve, what are the ones that are relevant to the ICAPS community? So the reason why that my group does work in planning is to try to enable kind of the creation of autonomous systems where we can specify a set of goals that they're trying to achieve, and then the system achieves those goals by using some action model. The way that it's going to do that is it's going to be using some form of generative planning to generate a course of action to try to achieve those goals. Okay, so the kind of the motivating example we've done for this is that if you look at how vehicles such as underwater vehicles or drones are commanded today, then typically they're commanded by giving them a set of waypoints, and then the system either follows those waypoints, right, or executes some mission abort script. The concept is to be able to give the vehicle a set of goals, right, such as a set of locations that you want to start at, places that you want to go, and places that you want to return, and then have the system generate a plan to achieve that course of action. So I'll give you a simple example of this kind of using a classical planner. Unfortunately, the movie's broken at the moment. So here's an example of a mission where what we have is we have an air vehicle here. What we want it to do is we want it to put out the fires that these two put out a fire at this location. Let's see where the other, here's the second location. In order to put out its fire, it needs to be able to have fuel. It needs to be able to get some water. It needs to go over the fire. It needs to drop water on it, right? It needs to go back and get some more water, put out the other fire, and then it needs to return to the base. So that's something at that level, which is a very good classic planning problem or a generative temporal planning problem. So we can describe the different actions within PDDL, right? We can have the system generate a plan, execute it, and then we can have a kind of replan along the way. It is the case that in order that in PDDL we can say things like if you're over the lake and you don't have some water, then you can pick up the water, right? So you can put in those kinds of actions. You also do need to do some path planning. So you need to do some roadmap path planning on top of the activity planning. So here's kind of a system that does this. In this case, what we have is a Java-like language which specifies the set of goals, and then under the hood to execute these programs, we're going to use a generative planner, right? So in this case, we have an object which specifies the different entities within this problem. So we have a UAV, we have 2 lakes, and we have 2 fires. Our mission is simply that we want the first fire to be out, the second fire to be out, and then we want the UAV to be back at the base and have it to be landed, right? So it looks like a very simple program, but much simpler than a series of waypoints that we gave before. And what this program is simply doing is asserting states of these different objects over periods of time. And then if you look at the definition of these objects, then they specify the states. For example, this says that Lake 1 is a new lake and its location is at a particular location, that there's a fire and the fire level is high, for example. Okay? And then here is simply a description of, in an object-oriented paradigm, here's a set of methods describing the different actions that the vehicle can take. This simply says that if the vehicle takes off, then it needs to be landed to start, and at the end it's flying. We can do that for a set of methods. Okay. So in this case, you can say, why are we doing this? I mean, really what it's just doing is it's a set of syntax for PDDL. In this case, what we're doing is we're providing for the operator a simple object-oriented paradigm, right, where you have a vehicle, right, it has a set of primitive actions that it can perform, right, and it changes the state of the world. Normally what we could do is in a PDDL problem, we define the set of state variables and then set of descriptions for each of the actions, the preconditions and effects. And what we're simply doing is to be able to provide this within an object-oriented paradigm where every object has states and it has a set of methods which are state changing. But what we know is that that's really a problem which is easily encodable in PDDL. So given this description, right, which is fairly simple, right, then if the movie would work, right, then you simply say execute and then the vehicle moves around, right, and achieves the goals. In order to do this, the commanding is very simple, but it did need to do both activity planning and it did need to do motion planning. It needs to do motion planning at the level of roadmap path planning, right, but also needs to fly the vehicle and deal with the dynamics. Okay, so general planning is very relevant, but we do need to deal with the continuous dynamics and we need to deal with the uncertainty. Okay, so why isn't classical planning enough? Okay, so these are things we know, which is in addition to deal with discrete states, we need to deal with the continuous, right, state of the world, right, and we need to deal with the coupling of the dynamics of the vehicle between its environment and the higher level states that we want to achieve. We do need to meet deadlines, right? For example, we can't have the fire raging out of control, so we do need to do with temporal planning. So these together mean that this is a hybrid planning problem. The world has disturbances. We do want to be able to replan to adapt to those disturbances. So we do want to be able to do continual planning, right? So leave planning and execution. But we don't want the system simply to adapt to disturbances, because you could walk yourself into a situation where you can't get out of. So there you really need to deal with avoiding situations that are too risky. And we need to deal, when we're dealing with risk, we need to deal with both the uncertainty in time, the uncertainty in state, and how those couple together. Okay? So if we take this as a motivating example, right, then our central issues are going to be how do we deal with uncertainty in state, which is my half of the tutorial, and then how do we deal with uncertainty in time, and then how do we deal with the coupling between the two. Okay? So that gives you kind of these two parts, which is we'll deal with state with a slight coupling in time, and then we'll focus on time. Okay? And then the architecture that we'd be thinking about is commonly when we take an activity planner and we add in time and continuous variables, then we still have a general component, which is doing some form of heuristic forward search. Right? That's going to couple together with something which is solving a temporal problem. In our case, it's going to be a probabilistic temporal problem to check consistency. Right? And then we also need to be able to have that activity planner couple into a trajectory planner, right, to be able to map discrete states to motions. And so these are the two pieces that we'll talk about, but we kind of assume that you understand this overall context. Okay, so can you bring up the view of the second part? So do we have any questions at this point? Good. Okay, so this is just kind of context setting. What I'm now going to do is to kind of dive into trajectory planning. Right now, how many of you know about model predictive control? Okay, and kind of trajectory optimization? Not so much. Okay, so what I would do is that I will kind of first look at not the stochastic case, right, but the deterministic case, and kind of introduce model predictive control. But hopefully, I can do that quickly, and then I'll focus into the stochastic. But I just want to make sure that you do have that context, right? Okay, so. Trajectory optimization is simply that you have some vehicle, right? You have some, and what you want to do is you want to determine a trajectory that you want that vehicle to go through, right? Or some physical state with a set of continuous variables. You were trying to come up with some trajectory over those continuous variables. We have some dynamics that we need to satisfy, right? So we want to find a trajectory subject to an initial state, right? And the dynamics, usually we have some goal. In the simplest case, it is some target that we want to achieve at the end. We'll, in addition, have some exclusion zones, right? So some unsafe regions that we want to avoid, such as a set of obstacles, right? And then we'll have a set of actuation constraints, which is kind of the range over the control variables that the system is allowed to be set. Okay? So in the simplest case, it's just initial state and a goal state plus dynamics plus actuation constraints plus safety constraints. Okay? And you can frame that as an optimization problem and solve it. And I'll go into that in coding at the moment. If you talk about as temporal planning is we use a general planner, it generates a plan, and then we want to execute that plan by controlling a set of vehicles. Then when we control that set of vehicles, it needs to not only respect the set of constraints that I specified here, but it also has to satisfy the plan. So in the trajectory optimization problem, we somehow need to be able to take the original plan and encode that as a constraint to the trajectory optimization solver. That's not something normally that model predictive control will deal with. But I just spent a little bit of time about that encoding. So we'll refer to that as a goal-directed model predictive control. Okay, so in general, trajectory optimization is simply that you have some state space, right? Defined by P. You have a set of feasible states, capital P. You have some objective functions such as maximizing science utility or minimizing fuel usage, right? And it's simply an optimization problem of find the path P, right, which minimizes, right, the cost subject to the constraints P, okay? If you then kind of instantiate that, right, then typically what you do is you say for these problems that you have a set of state variables X plus a set of control variables U, right, that you plan over a fixed horizon or a finite horizon, and we'll represent that by T. And implicitly in this, we're going to use a discrete time formulation, right? So we're going to discretize time, and then T is the number of time steps. Okay? So the total time is going to be T times some delta, which is the size of each time step. Okay? For the purposes of this tutorial, we're just going to talk about a linear dynamical system. So in this case, we're using a discrete time formulation where we say that the state at time k plus 1 is a function of the state at time k plus the control input at time k, and we're going to say that these just combine linearly. Okay, So this is a set of linear equality constraints. I mentioned we had actuation constraints before. So this should be mu here. And so this simply says that the control input, which are the decision variables, is constrained to be between some maximum and minimum. And those can be a function of time as well. Okay? And then we have some objective function. And the objective function is looking at the sequence of states. So it's a path constraint. So it's looking at the state trajectory together with the control sequence. Okay? And then the output is simply going to be an assignment to x and mu, right, which satisfies the vehicle dynamics, the actuation limits, and then the temporal plan that it's trying to execute. And I'll introduce that in a moment. Okay? So how do we specify the temporal plan, right? Well, normally we just have some plan which would say, I want to go from A to B, right? In general, what we're trying to do is we're trying to constrain the state of the vehicle. So for example, what we're really doing is to say, for example, that I want the vehicle to be over the fire, right, for 5 to 8 minutes, right? And over the fire corresponds to being in this region, okay? Likewise, we will want to be able to say that we want the vehicle to never collide into the obstacles. So we're saying that throughout the duration of the mission, we want it to be outside of this region. So what we can do is we can think of a plan as normally having a set of activities and temporal constraints. In our case, the activities are constraining what are the allowed and disallowed constraints over that interval of time. And then we're specifying temporal relationships between those activities, which we'll refer to as episodes historically. Okay? So a temporal plan which constrains state, we refer to as a state plan because we're not specifying a specific state, but we're giving a set of acceptable states, right? Then we use the term qualitative state plan. Okay, so a state plan is simply a set of episodes, right? Each episode has a state constraint, right? And a duration between a start and an end time, together with a set of simple temporal constraints relating the start and the end times, right? So you can think of this problem as a simple temporal network between events plus a set of state constraints, right, which hold between events. Okay, does that make sense? Okay. Now, in the encoding that I'll give here, the form of the state constraints in general can just be any function, which is basically giving you the allowed states at each point in time throughout the duration of the episode. We'll use a simpler encoding for this tutorial where we'll simply say that you can either have some state constraint which holds throughout the duration of the episode, it holds at the beginning or holds at the end, right? But that's just for pedagogical simplicity. Okay. So if we then go back and look at our problem, right? So what we now is we have the trajectory optimization problem where with the utility, the dynamics, the actuation constraints, and the qualitative state plan, we want to frame an optimization problem here, which provides us a trajectory which satisfies those constraints. So the first part of the formulation is what we saw before, right? So we just give the dynamical constraints. We give both the actuation constraints. The obstacles we can represent as a set of spatial constraints. I'll give you an example for that. Classically, you give a start and a goal. We'll replace that with a qualitative state plan, and then we have the actuation constraints. So let me, I see this isn't my version of this. So I won't kind of bother going into encoding the dynamics. You can look at that kind of offline if you'd like. What we'll do is to talk just a little bit about encoding the state constraints. So what we'll do is we'll think of the regions where we want the vehicle to be or to avoid as a set of polygons, right? So we can describe the polygon as a set of boundaries, okay? And so if we want to stay within some region, then the way that we express that is simply a conjunction of inequality constraints, where each inequality constraint corresponds to one of the boundaries, right, on this obstacle. If we have a more complex region, then you can use algorithms to basically construct a tiling of that region in terms of a set of polygons, right? And then you can simply say I want to stay in this region by conjoining this set of constraints. If you want to avoid an obstacle, right, so you want to be outside of it, then you simply want to negate these constraints, right? So if you negate this, then by De Morgan's, right, then this conjunction turns into a disjunction, and then you just flip this inequality. So the key difference here is that if you want to work within some convex region, it's very simple. It's just simply a conjunction of inequality constraints, and you can encode this as a linear program. If we want to avoid obstacles, which is normally the case, then it becomes a disjunctive linear program. And that disjunction is what makes the problem harder to solve. And on my part, we'll first look at the conjunctive case, and then we'll look at the disjunctive case. Okay, so the other part is in encoding the qualitative state plan, right? So that's fairly simple, right? So we have a set of temporal constraints, right? So we have a set of events, a set of temporal constraints. Those are simple temporal constraints, which we can introduce as a set of inequality constraints. And then we also need to introduce the state constraints, which hold over the episode. Okay, so for each event, right, in the plan, we introduce a real valued variable for it. Okay, and then we encode the simple temporal constraint, which is a lower bound, upper bound, as a pair of inequality constraints. Then for each episode, we have to be able to encode the three cases of remain in, start in, and end in. Okay, so if we start kind of first with remain in, right, then remain in simply says that throughout the start time to the end time, the state constraint needs to hold. So we simply have an implication which says that if the current time is between the start and the end, then enforce the state constraint. Okay. If we're going to use a mixed integer linear program, then we have to encode implication, right, through integer variables or binary variables, but that's fairly standard. Okay. If we then go to, for example, end in, right, then the thing we have to deal with this case is at the start and the end times we didn't discretize. So we use them as real valued variables, which is what we typically do in simple temporal problems. But with respect to the dynamics, we have used a discrete time formulation. So we can't say that will end exactly at the time of this event. What we need to do is to find the integer time which is closest to that event. So in this case, we simply say that if the current time is within half of a time step, right, of the end time, then ensure that the state constraint holds. Okay? And you can do the same thing for encoding both start in and then end in. Okay? Okay, so that's how we'll take a temporal plan, right, which an activity planner generated, and give that as a set of requirements to a trajectory optimization algorithm, then it'll solve it. Now, given that set of constraints, right, I gave you a mixture of logical constraints and a set of algebraic, linear equality and inequality constraints. To solve that, we could either solve that directly as a disjunctive linear program. So we reduce it to a clausal form and then solve the disjunctive linear program. That's what Ballas kind of back in the 60s first kind of proposed. But what he then said is rather than reasoning about the logic representation explicitly, we'll reformulate that into a binary integer program using kind of big M variable encodings. And then you solve this using a binary integer programming or a MIP solver. So in most of the cases here, we'll just use Cplex to solve it. We'll do that standard encoding. Okay, but I'm not going to go into that here. So if you solve these problems, right, then there will be a couple issues. The first one will be that if you try to plan over the full duration of the mission, this becomes too complicated a problem to solve. So instead of solving the complete problem, what you do is you'll solve it over a horizon, right? You'll solve it during that horizon, and then you repeat. Okay, so you just decompose it into a set of horizons, and then you solve it. The issue is that you want to deal with the uncertainty, right? And you want to be able to adapt to the uncertainty. So you keep resolving the optimization problem. So in model predictive control, what you'll do is that you'll have plan and execute for a region. You'll generate a plan for the next, the next horizon, and you'll start executing that. But as you start executing, you replan based on the new state update. And then as soon as you have a new plan, then you just swap to that new plan. Okay, so as the system deviates, right, you quickly replan and then you come up with a new plan. So the basic notion of model predictive control is that you plan over a finite horizon and you're constantly replanning, and as soon as you generate a new plan, then you shift to that new plan. You plan over a longer horizon than the portion that you execute so that you have some prediction into the future. Okay? Okay, so that's kind of the short version of model predictive control. Okay, so what I've given you at this point is just kind of introduce the idea of model predictive control, how we will do an encoding as a mixed integer linear program or a mixed logic linear program, and the idea that it will kind of repeatedly plan over some horizon. If you look at the problem formulation when you're doing a model predictive control, also known as receding horizon control, because you have a fixed horizon, but it keeps moving over time, then what we do is we start with the encoding that we gave before, where we've added in the qualitative state plan, but the goal state is beyond our horizon, so we remove that as a constraint because we can't achieve that within the planning horizon that we have. Instead, we remove that as a constraint and then introduce that as a cost to go function, right? So basically it becomes in our context, a heuristic, right? So we have some heuristic estimate of how much work it's going to take to achieve the goal. And that's something that the planning community is very familiar with, particularly in the discrete world. In this case, it's dealing with the continuous world. And there's a whole body of work on coming up with good functions. Okay. So what this would have shown you simply is the execution of a plan which focuses on the model predictive control, right? And then what you've seen is that this vehicle is moving around, right? So it's trying to achieve the activities in the plan, right? But it's using the dynamics to do an optimization of the vehicle. And what you'd see is that it's planning over a short horizon. It's constantly updating. So if you, at least, maybe about 8 years ago, if you were solving this problem, you could plan over about time horizons over maybe 7 or 8 time steps, right? And do the planning in real time. That's increased by, maybe a factor of 4 now over the last few years. But the point here is that the model predictive control is going to be planning over fairly short horizons, right? And then anything beyond that horizon is more at the activity planning level and is dealing with the kind of adapting to the disturbances. The algorithms have gotten better, right? But when you deal with these stochastic problems, then the problem becomes much harder. I'll give you some benchmarks on that. Okay, so that's the idea of trajectory planning, right? Now what I want to do is what this tutorial is really about, which is talking about bounded risk. So I'm going to take the same problem, but I'm going to talk about imposing chance constraints. Okay, so if we talk about the uncertainties we have, then the uncertainties we will have are a couple of things, right? So there's going to be uncertainty in the actuation, which is, for example, the wind disturbance. That's an additional control input, right, which is not under our control. There's uncertainty in the sensors, right? So they may be giving us an inaccurate state estimate. And then there's inaccuracies in the model of the world. So for example, we don't know exactly where some obstacle is. If it's a weather system, that weather system may be moving and we don't know exactly where that weather system is, but we know that we want to avoid it. So we need to deal with the uncertainties in each of those parts of our formulation. But if you look at the trajectory optimization problem, then that corresponds to your uncertainty in your control variables, uncertainty in your safety constraints, actuation constraints, and then your dynamical model. And then in a hidden state problem, which we haven't given it, then you have the uncertainty in the observables as well. Okay, the risks are going to be both violating some safety constraint and violating your temporal deadlines, right? We just have temporal constraints and we have state constraints, so we have to deal with the violation of each of those. Okay, so one way we can deal with this is doing kind of robust model predictive control, right? Where what it will do is it will identify a set bound on the uncertain variables, and then you guarantee success within that range. And we'll talk about that for a moment. And then the other one is the probabilistic formulation. So classically within control, what they don't want to do is they don't want an explicit reason about the uncertainty. So instead what they do is they say that we'll assume some bound, right, on the uncertain variables, right? And S and U is a bound on some temporal variable. It's just a real value variable with one dimension. In a system where we're dealing with continuous state, we simply expand that to an n-dimensional region. It's typically an elliptical region. And then we'll say is given that the uncertainty is within this bounded region, we can use the dynamics to say, kind of predict how that region grows over time, but each of those are sets. And then if we introduce, for example, a set of obstacles, then what we'll do is we'll say, come up with a trajectory which guarantees that for all possible states that the system could be in, that they don't violate these constraints. And you can formulate that basically as a minimax problem, okay? And that's fine if uncertainty is bounded, right? Or you can do a good job of setting these bounds. But for unbounded uncertainty, which is what the world is typically like, then instead you give a probability distribution on your initial state, you give a probability distribution on the disturbances at each point in time, and then from that you compute a belief state, right? Which is telling you the probability distribution of the state, over the horizon. Okay. Now you can go back and forth between these, right? So that the chance constraint says that the probability of success is, for example, 99%, right? Then what we can do is we can compute these distributions. We can then take the ellipse, which corresponds to 99%. This problem maps into this problem. Then we can use these algorithms. And we're going to leverage that idea in this tutorial. Okay, so when you incorporate uncertainty, let me just mention that what we're doing is we're using a linear time invariant model, right, where we're going to be using additive noise, right? So you can add in noise. The other thing to do would be to have multiplicative uncertainty, right? So in this case, For example, if you had model uncertainty, then the model will be these state matrices A and B. If you have additive noise to those coefficient matrices, then the corresponding thing is it has a multiplicative effect on the state variables, right? We're dealing with additive noise. It's both kind of the most common case, but it's also the thing that's most tractable. We'll deal with that approximation error by constantly replanning, right? So we do have the benefit, the fact that we can be somewhat robust to approximation error because we're constantly replanning based on state updates. Okay, so let me just say a little bit more about bounded uncertainty versus probabilistic uncertainty. So in the bounded case, there's a couple things that you could do. So what you could do is to minimize the worst case cost. So in this case, what we do is to find the control value, which minimizes the worst case subject to satisfying our safety constraints. Another way people would typically do this is to ignore the host set of states and then just look at the nominal trajectory and try to minimize the nominal costs. You could also compute an expectation, but we don't have probabilities, right? So if you want to do something more like an expectation, then you have to do some ad hoc version of those. Okay. So the fact that we have ignored the probability distribution of the set of states kind of limits how we can express utility. In the case of a stochastic formulation, right, then as I mentioned before, one could take a utilitarian approach, right? So what we'll do is we'll maximize expected utility. So this is our random variable here. And then what we'll do is that we'll incorporate the probability of failure as some penalty against cost. In our case, what we're doing is we're looking at chance-constrained formulations. So what we're instead doing is saying that the constraints are a function of a random variable, right? And the probability of violating those constraints are within some bound. Okay. So I'm going to give you, well, let me kind of bounce by this. Okay, so in a chance-constrained approach, right, then what we'll do is we'll specify, for example, that the probability that we will collide into one of these obstacles is at most capital delta, right? And then we'll compute a trajectory, right, where the sum over those trajectories, right, which violate one or more of these constraints, that is, collides into one of these obstacles, is less than delta. And then we'll find the optimal trajectory, right, which is less than delta. So if we now adjust delta, right, then we'll get different levels of conservatism in the algorithm. So if we say that we disregard the probability of failure completely, right, then or we use a purely deterministic formulation, right, then here's the trajectory that the deterministic optimization would come up with, right? If we then say for example, we want to accept a 10% probability of failure, right, then we see that it backed away from the obstacle a little bit. As we keep kind of reducing the risk, right, the probability of acceptable failure, it keeps moving further and further away from the obstacles and starts moving more towards the middle, which is more what you get if you're using a Voronoi diagram to do path planning, right? This is more like what you would get if you're using a visibly graph approach. And then depending on the conservatism, eventually the algorithm will decide to avoid the obstacles altogether. Okay? So you kind of get the desired behavior from this formulation, which matches your intuitions. Okay, so in our case, how do we specify the chance constraints? So what we said is that our mission description is going to be some qualitative state plan, and they have different features. Part of those constraints within the qualitative state plan are safety. Others are kind of achieving our primary goals. If we put a higher value, for example, of life than getting to the conference in time, then the chance constraints that we want to have for keeping safe versus reaching our destination will have very different risk levels. So the important thing to do is to be able to express different levels of risk for different subsets of the activities. So in our case, what you can do is you can take any subset of a qualitative state plan, which is basically a set of episodes and temporal constraints, and then you say that the probability of violating that set of constraints is in some risk bound, and then you specify different risk bounds for different subsets. So we just have multiple chance constraints, but each of those chance constraints is global in the sense that it applies to multiple constraints. Okay? Okay, so the particular algorithm that I'm going to give you, refer to it as PSU. The deterministic case was called SULU, but we're going to add in probabilities and uncertainty to it. And what I want to do is to go into that formulation. I'm going to kind of back off of those examples. But the problem is now to take a quality state plan as input with chance constraints plus a dynamical model, right? But with probability distributions over the random variables, and then we want to come up with a trajectory, right, which satisfies the chance constrained qualitative state plan. Okay, so in order to do this, what I'm going to do is I'm first going to give you an overview of a couple different approaches to doing stochastic optimization, right? And then I'm going to focus on the particular technique that we've been developing called risk allocation methods. But I wanted to do due diligence, right? So when you look at chance constrained problems, so the stochastic optimization community has looked at this quite a bit. Typically what they do is they use sampling-based approaches, right? So for example, within the planning community, techniques like UCT are sampling-based approaches, right? Where you take a number of samples and then you formulate the problem as a function of that set of samples. Scenario trees is one kind of approach to that. I'll just give you another example called particle control. But what you do is you take a stochastic problem and you determinize it by picking a set of samples and then writing a set of deterministic cases over those samples, right? But the size of the problem grows in the number of samples, and that's kind of the problem with it. Okay, so if we do the trajectory optimization problem, and we have a set of random variables, right, which are going to be our initial state and our noise terms, then we can simply sample each of those variables, right? So for example, the initial state, we take a set of samples, or consider them to be a set of particles. We'll do that for each variable along the way, and then for each sample, we'll consider that to be a scenario, right? And then we'll frame a trajectory optimization problem for that scenario, okay? So we can do that. So what we'll do is we'll describe the trajectory the vehicle will go through for that particular scenario. Now, it's a function of the random variables which we've determinized, but it's also a function of the continuous control variables, right? Which we haven't determined the values of those control variables, right? The problem with the optimization is to determine the values of those control variables. So when we describe this trajectory, we describe it as an analytical function, as a function of the continuous control variables, okay? And we can represent that by a set of linear equality and equality constraints. So we can then talk about solving that one optimization problem, right, subject to satisfying this set of constraints. The thing that we need to deal with is the fact that we want to be able to come up with a control trajectory which applies to all scenarios. And not all scenarios have to succeed. They have to succeed according to the chance constraint. So what we'll do is that we encode the trajectories for each scenario. They're coupled by saying that the assignment to the control variables have to be the same through all the scenarios. And then the way that we encode the chance constraint is to simply compute a statistic, right? So we simply look at the number of scenarios which satisfy our constraints, right, versus those that don't. And we impose a constraint which says that has to be bounded by the chance constraint. Okay. And so we solve that problem, right, as we kind of know that as the number of samples approaches infinity, then it becomes an exact approximation. But that may be nice to know from a practical standpoint. That's not terribly useful. So these problems these kinds of sampling-based approaches do not scale very well. It was sufficient for the underwater vehicle problem where we were just trying to determine the depth of the vehicle because it only had one variable replicated over the time horizon, but it was a one-dimensional problem, right? The technique doesn't guarantee that you satisfy the chance constraint because it's doing an approximation, right? So under that approximation, it can be arbitrarily close or away from the chance constraint depending on the number of samples you take. What we really want to do is to make sure that the algorithm doesn't take more risk, right? We don't want it to be too conservative, but the way that it should handle approximation error is to be more conservative. The other thing is we don't really want to do these sampling-based approaches, right? Because it just simply grows the number of state variables as a function of the number of samples. So instead, what I'm going to talk about are techniques which are not sample-based. And they have the common feature that they're going to take a stochastic problem and reformulate it into a deterministic problem, right? But in doing that, it's not going to take a number of samples, so it's not going to kind of dramatically increase the number of variables, right? And the way that these algorithms are going to determinize the problem is basically to build in a safety margin, but in a more principled manner. So the first technique people explored earlier on was an elliptical approximation, right, which kind of mapped a stochastic problem to a robust control problem. Okay, and so in this case, right, if you say that the probability of failure is, for example, 1%, right, then what we'll do is that we'll have a probability distribution defining the state of the system. Here I'm just going to look at state as opposed to a state trajectory, right? And then if we have the chance constraint which says that the risk is 1%, then we can look at the 99% ellipse here, right? And we say that we want to ensure that all the states within this ellipse don't violate the constraint. And then we'll ignore ignore the states outside of that region. So that ellipse, right, gives us a set bound, and then we can use the robust control techniques, right, to do the planning. So we take the probability distribution, we identify this ellipse, right, and then we solve an optimization problem which determines that that ellipse is feasible with respect to the set of constraints. Okay, so we've determinized the problem. The problem, so that's nice, right, and that was one of the first kind of more efficient approaches. One of the most significant problems with this is that it's overly conservative, right? Really what we wanted to do was to say that the probability that we would be in this region, right, is 1%. What it did was to ensure that the probability, right, that, but instead what it did was it also took this region here and said that, let's see if we can say it. So if you look at the integral here, right, what we're trying to do is to say the integral over this region here has to be less than 1%. What this thing said here is that the integral over this region here, or 1 minus this region here, has to be less than 1%. So in fact, the probability of failure is going to be 1% minus this area, right? So it's much more conservative. So this technique does not work that well, right, in terms of exploiting the risk that you've given. It's very conservative, though it is an efficient technique, right? But what we want to do is to be able to avoid this level of conservatism. So instead of providing basically a set bound over the continuous state variable here, what we'll do is we'll create a set point bound relative to the hard constraint that we're trying to satisfy. In the temporal problems, right, that Erez is going to talk about, we're actually going to shift more towards this kind of approach. But for this part of the tutorial, we're going to talk about how do I adjust this margin here with a bit of an extra safety margin, right, so that we're respecting the chance constraint. And that avoids this level of conservatism. Okay, so how do we do that? Okay, so here's the intuition. So the simple example that I'll give you is that we have a vehicle, right? Or some linear dynamics. We want it to go along a road. We want it to cross the finish line. If it crosses the finish line, and we're the fastest one to cross the finish line, then we win. If we hit any of the walls, then we lose, right? So those are our safety constraints. And then we have some uncertainty, right? So as a driver, the way we would deal with this is we'd have a safety margin, right? So we tell our kids stay 3 feet away from the curb or something like that at all times, and that's a simple heuristic, and that would give you the trajectory here, right? Okay, so what we want is an algorithm which can take the probabilistic formulation, the chance constraint, and build this safety margin. If you have the safety margin, then you can just plan a path in terms of the nominal variable while ignoring the uncertainty, okay? The thing is that if you look at different safety margins, then as we get to be better and better drivers, right, then we don't stay 3 feet away at all times, right? Then we get closer to the curb, right? And the reason why we do this in this case is it's more efficient. In this case, we cross the finish line faster if we clip the corner here, but we stay in the middle of the road, right, in the long parts of the road, because we don't really get any benefit of getting close to the curb here. If you look at the overall risk, and the risk is basically a function of the integral of this area, right? So both of these are taking the same amount of risk, but this is using the risk more effectively to achieve higher utility. So the way that we frame this problem is that what we're going to do is, given the probabilistic formulation, we're going to automatically synthesize the safety margin, right? So we're going to design the safety margin, but we need to design the safety margin amongst all the possible safety margins to find the one which maximizes expected utility. So we've now taken an original problem, which was to deal with an assignment to a set of control variables, and now what we're going to do is to solve an optimization problem both over the trajectory of the vehicle and the safety margins. Now the way that we'll design the safety margin is not explicitly, but what we'll do is we'll decide at every point in time with respect to each side of the road how much risk we're going to be willing to take. So given that I have a 1% probability of failure, which is acceptable, then at each point in time I have to say, what's the acceptable probability of colliding to this wall, and what's the probability of colliding to this wall? And then if I take those probabilities, which I'll do represent as lowercase delta, then the sum of those lowercase deltas have to add up to no more than the capital delta, which is the 1%. Okay? So does that make sense? Now, once I know how much risk I'm willing to accept at each point in time with respect to each constraint, then I can automatically use an algorithm to generate the safety margin, and it's a straightforward, though nonlinear calculation. Okay? Okay, so that's the intuition of what we'll do. And what we're mainly going to talk about here, so So we refer to that as risk allocation because we have this overall risk, right, capital delta 1%, and we're going to allocate or spend that risk at each point in time, and then we'll spend it with respect to each of the constraints. And so we need to do that allocation, okay? And so the rest of the tutorial will give you a whole range of different algorithms to perform that risk allocation, okay? Pass over here. So what I'm going to do is I'm going to kind of build up to the problem of doing chance-constrained trajectory optimization for a qualitative state plan, but I'm going to do it in steps, right? And the first one is I'm going to talk about the case where I have some trajectory that I want the system to go through, and my constraint is that at certain periods of time I want to go through different intermediate regions or waypoints, right? What's nice about this is that, and I'm going to ignore the obstacles. So in this case, I want to, at certain points of time, be within some region, which is a convex region. So I can represent this as a conjunction of linear inequality constraints. And so I can frame the trajectory planning problem as a linear program, as we saw before, but it's going to be a stochastic linear program, okay? When I introduce obstacles, which is the next step, then the problem becomes disjunctive as opposed to conjunctive. So I have to talk about how do we deal with stochastic disjunctive linear programs. And then the last step is to add in the temporal constraints. And if I have time, I'll touch on that briefly, or you can look at those slides. But then Erez is going to spend the time focusing on the uncertainty in time much more deeply. OK, so let's look at the conjunctive problem. So just remember, the deterministic finite horizon formulation was we had some horizon t, we had a linearized dynamics, and we replicated the linear constraints for every successive time step, right? So there was a set of different constraints, right? Our convex regions that we need to stay in are simply a conjunction of linear inequality constraints, right? In the case that we'll do next, where we're avoiding obstacles, then these constraints become disjunctive as opposed to conjunctive, right? But we're just going to look at this case first, okay? Where each C1 is a linear inequality constraint. To do the stochastic formulation, right, then what we need to do is to introduce a set of the noise terms, right? So we'll add in a noise term at each point in time, and then also an initial state distribution, right, as additive noise. We need to describe those variables. So for this tutorial, we'll assume that these are, Gaussian distributed noise, right? Okay, and then we also have an initial state estimation error, and then x has become a random variable at this point. Okay. We can't satisfy the state constraints, right? Given that x is a random variable with unbounded uncertainty, so we replace that with a chance constraint. Okay, so we simply said the probability of satisfying these inequality constraints is going to be 1 minus delta, where delta is the probability of failure. Okay, so that's our reformulation of the chance constraint optimal control problem, and you can take the encodings I gave you before and fold this into this framework. Okay, so how do we go about using the idea of risk allocation to take this chance constraint problem and turn it into a series of deterministic methods, right? So this is kind of the key idea at the level. So I'm going to first give you the intuition, and then I'll go back through the mathematics, right? So the simplest case would be that I have a problem with one random variable, x, right? And I have one constraint, and then I have a chance constraint applied it. So it's a unary chance constraint on a one-dimensional problem, okay? So if I took this problem, right, and I add in my distribution, right, so I have a probability distribution here, right? And the probability of failure is going to be the integral here, right? The set of states, right, which violate the constraint times the probability of each of those states. The requirement that I have is that the area, right, here needs to be less than 1%, right? So my constraint boundary is the point at which this area is equal to 1%. So I'm simply going to write a new constraint which says that the probability, an inequality constraint which says that the probability, right, of this area being, that I have guaranteed that the probability of this area is less than 1. And I'm going to write that constraint in terms of the mean here, right, and then the variance. Okay? So here's my mean variable, right? And then I'll have some variance. Okay? So I can come up with then an offset of x, right, with respect to this original constraint, right? I'll denote that by, this should be m, right? We're having to use an old version of the slides here, the video problems, right? So think of this as being some m, and m is a safety margin, right? And I'll give you the function which defines m in a moment. But basically what we do is we define a new constraint, which is going to be a function of the mean value of x, right? Right? And it's simply going to take the original constraint as a function of mean and offset it by some safety margin. And it's going to be an inverse cumulative distribution. I'll give you the form of the equation in a minute. Okay. So that's the idea, right, in the first case. So the takeaway lesson is if I have a one-dimensional problem with one constraint and then the risk is on that constraint, then it's fairly straightforward to compute an offset to determine the problem. It's guaranteed that that will satisfy those chance constraints exactly. Okay? But we want to have multiple variable problems and multiple constraints. So the next thing is I'll introduce a multivariable problem. Right? So in order to handle a multivariable problem, it's not that hard. What we do is that we project that onto, we basically compute the distance of the system state relative to the constraint boundary, right? So we compute the normal, right, to this boundary, and then we kind of repeat what we did. So we now have a one-dimensional problem, and then we just repeat the calculation that we did before. And that's not that hard to do. Okay. The real issue then is how do we deal with multiple constraints, okay? So if we knew how much risk that we were going to take with respect to each variable, right, then what we could do is to just apply what we've learned before, right, and compute the offset with respect to each constraint. The thing is that what we have to do is to be able to say how much risk do we associate with each of these constraints. So what we'll do is we'll introduce a set of risks with respect to each constraint, lowercase delta, and then we'll require that the sum of those deltas are less than the capital delta. Okay? And then these are variables, right? We don't know the exact value because there's multiple assignments. So these are not constants anymore. They are continuous variables that we need to deal with. Right. Okay, so we simply say that the sum of these, right, have to be less than, I should say delta. Or in this case, since delta is 1, then we say this less than 1%. Now there's an issue here, right, which is that we have introduced some conservatism, right? So we've used Boole's inequality to say that we've assumed that the events are independent and hence they're additive, right? So we have the net effect of double counting, and the double counting corresponds to this case where we're violating these both constraints. So we count them twice. Okay, so that area is the amount of conservatism that we're introducing in this algorithm, but that conservatism is much less than what we saw previously in the elliptical approach, which is that we're counting this area where we shouldn't. Okay? But there is that conservatism. It is nice that it is conservative, so it isn't going to take more risk than you wanted to have, right? Which is what the sampling-based approaches would do. Okay. So let me just kind of go back through the intuitions and go to it mathematically. Okay. So what we do is we start with the joint chance constraint here, right? So we have a set of conjunctive constraints, so multiple constraints. We have multiple random variables. So what I'm going to do is to take the conjunctive constraints, break them into a set of unary constraints over n-dimensional variables, and then turn them into single-dimensional variables, right? And then finally determinize it. Okay. So that's kind of just going back to the steps that I had before. Okay. So the first one is applying Boole's inequality. We introduce a set of lowercase deltas. We take the sum and say they're less than capital delta. Okay. And so that's what we've done here. So we've introduced a lowercase delta, right? And then what we've done is we've taken the probability of a conjunction of constraints. We've moved the probability in and the conjunction out. So now we have the conjunction of chance constraint as opposed to chance constraint over conjunction. Okay? So at this point, right, what we do is we have a chance constraint with respect to each constraint. In our finite horizon problem, what that's done is it's moved the chance constraint within each time step and within each constraint within each time step. Okay? And then we've summed the lowercase deltas, and we have the conservatism that we've given before. And then since these are probabilities, we require each of these deltas to be positive. Okay? So that's what we're doing there. Now the thing to notice here is this capital delta was a constant, right? So computing the safety margin, I didn't give you the formula yet. It's going to be a nonlinear function, and that wasn't a problem because delta was a constant. We plugged this into a nonlinear function, it gives us another constant, and the optimization algorithm doesn't have to deal with it. The problem here is that delta is a variable. It's a decision variable. We're making some decisions over. The safety margin is going to be a function of delta, which is a non-convex function. Right? So that's what's going to make the problem harder. So along the way, I'll go from a stochastic problem to a deterministic problem, but it's going to be a non-convex problem. And we don't really like that, so we'll have to deal with that. Okay. Okay. And then we've added these decision variables here. So this is how we've reformulated the chance constraints. If we then take it back to our original problem formulation, then here's our original stochastic formulation, right? We had the random variables here, right? We had the chance constraint here. We replaced the chance constraint, right? So we now have this unary chance constraints. We've introduced the delta here. Since our decision variables, we introduce them here. Okay, so we're minimizing over delta. Does that make sense? Okay. So we either solve this as one optimization problem, that's what I would do first, or we're going to solve this as a master and a subproblem, where the master will be searching over the decision over the risk variables, and then these will be the control variables. Okay. So we still have a stochastic formulation. I haven't gotten rid of these, but we do now have a unary chance constraint. So the next step is to get rid of these. Okay. So in order to do this, right, we basically use the analysis that we had before. Right? So we have a univariate Gaussian distribution. Okay. Using the analysis that we had before, right, then we compute the safety margin, right, which is a function of delta. That safety margin is basically going to be the inverse cumulative distribution here. I think so. We'll just denote that m sub t as a function of delta. Okay, and then we introduce the deterministic constraint, which looks like we had before, but instead of this being a constant m, it's a function m of delta. So then you ask, what does the form of this look like? So that's what it looks like. I'm not going to go into it for the purpose of this tutorial, right? But we're taking the inverse of the cumulative distribution of Gaussian, right? So we're just ensuring that we're trying to find the value of delta such that the integral, right, of the region which intersects with the constraint is equal to the risk variable. If you look intuitively what's going on given this formulation, and I'll go back and show you the form of m, then the nice thing intuitively is that in this constraint, the constraint is a function of the mean. So we basically determinize the problem by looking at the nominal trajectory while ignoring the uncertainty, right? And then m of delta here intuitively corresponds to the safety margin at each constraint and at each time.
I understand you're checking the constraint only at those discrete points, so we don't have we'd have to make sure the time step is small enough that we don't have to worry about in between.
Right. So in this, that's an excellent question. Right. So in this case, we're doing a discrete time formulation, which is typically what people do in model prediction control. In fact, what we're doing is at each of those points in time, we're guaranteeing that the chance constraint is satisfied, but we're actually not ensuring anything in between, right? And I would have included how we'd address that in this tutorial, but we're still publishing that, right? So in fact, what will happen is if you discretize this, you pick this time point and this time point here, we would make sure that we satisfy our safety constraint here, our safety margin here, but in between, we haven't said anything. So the danger is the algorithm could flip the corner here. Okay, so we designed another set of algorithms, right, which will guarantee, right, that although you're doing a discrete time formulation, that the continuous trajectory that you move in between the time points will satisfy the risk bound as well. So that's going to be honest. Does that make sense? When we deal with temporal problems, then time will be continuous as opposed to discrete. So in the work that Erez talks about, that won't be the issue. Though a lot of the work in the constraint programming community and scheduling is they do discretized time. So there is the issue if you discretize time, what risk have you implied by doing that? Okay. Okay. So if you then take this formulation, right, then we now want to remove these random variables, right, through this reformulation. Okay, so we do that. Okay, right. So here we no longer have the random variables. X is a deterministic variable, right? Okay, we have the safety margin, which is a function of delta. If you now look at the form of that function, and this is the form of that function, right? So in general, it's non-convex, right? But if we see the amount of risk that we're willing to accept is 50% or less, right? Then we're in this region, and then this region is convex. So it's not linear, but it is convex. Okay? So we can take this problem, we can impose the constraint that the risk of failure is less than 50%, and under that constraint, we can frame this as a deterministic convex optimization problem. Okay? So that's the first way that we solve it. Okay, so it's a convex problem over a set of continuous variables in the convex case, right? Or if we add in obstacles, right, then it becomes, for example, a mixed integer, nonlinear but convex problem. Okay? And in this case, it's guaranteed to find the optimal solution subject to the conservatism that we got. Right, so that's the first idea. Right, and so those cases where the problem is sufficiently well behaved, then you can solve this problem using conventional algorithms. Exactly. But calling it a convex solver is not. Okay. So that's the first idea. The second idea, introduces the notion of solving this problem iteratively. Right. So we said we have a set of risk variables, and then we have a set of control variables. We can either solve that all at once as a single optimization problem, or the other thing that we can do is we can have an outer loop problem where we assign the risk variables, and then once we've assigned the risk variables, then we come up with the control trajectory. The reason why we would want to do that is that, remember, the complexity of this problem, the alternative convex problem, was the fact that we had to encode the safety margin, right, as a function of delta as a variable. If we, in a master problem, right, if we can assign this delta, right, and then we solve the subproblem of assigning control variables, then this is replaced as a constant, right? So this problem is in fact a linear program, right? The original formulation was a stochastic linear program. That's much more manageable. Okay? So the second idea is going to be iterative risk allocation, which is actually the first argument we came up with, where we first assign a set of the risk variables. Given those, right, then we formulate a linear program. We solve that. We look at where the solution could be suboptimal, and then we use what we learned from that subproblem to come up with a new assignment. Okay? And in the temporal tutorials, we'll be actually doing an analogy. The Erez is we'll do an analogy to both of these approaches in the temporal case. Okay. Right. So the idea is that what we're going to do is we're going to start with just a stupid safety margin to begin with that's easy to compute. So what we're going to do is we're going to start by distributing risk uniformly at every point in time. So every constraint gets its fair share. Once we do that assignment, then we have a linear program, right? Okay, based on the equations in the previous slide. We solve that optimization problem, and we come up with a trajectory. We say, okay, well, where was this good? Where was this bad? Where do I want to reallocate the risk? And then we'll do this again, and then we'll frame a new problem, right? And the property will be that we'll have a series of risk allocations, and each risk allocation is guaranteed to not worsen, right, the utility. Right. Okay. We can't prove that it'll converge to the optimal system, but we can show that it does increasingly better. Okay. Right. So ideally, what will happen is we'll go from this safety margin, and then we'll design this. So how does the algorithm do this? So what's happening at each step? So here's the algorithm that's fairly simple to implement. Right? So we start with the uniform risk allocation, right? So we do that. We compute the best path. And then what we do is we analyze the problem and say, where did we spend the risk and where we didn't? Okay? So in the case where this trajectory hit the safety margin, then we used all the risk, right? In this case where we don't hit the safety margin, then we didn't use risk, right? We had allocated an amount of risk, right, that we didn't need. So what we'll do is to say that if we take more risk here, then the safety margin becomes less, right? Because more risk means less safety margin. That will give us higher utility at this point. And so we'll take risk away from these points and give the risk here. So this corresponds to any time that we hit the constraint boundary, that corresponds to the active constraint. Where we don't, that's inactive constraint. So what we'll do is we identify the active constraints, we identify the inactive constraints, and then we take away a percentage of the risk from the inactive constraints, give them to the active constraint, and then solve the problem. Okay? And that's just what it's doing, right? So it decreases the risk at the inactive constraints, which grows the margin, right? We give that, right, to the active constraints, right, which reduces the safety margin, right? And then we solve the optimization problem. Okay? And that's what we repeat. Okay. So that's what iterative risk allocation does. Now the nice thing about iterative risk allocation is if we have an algorithm which solves the deterministic problem, right, then at some level we can treat that as a black box. So we can take whatever that problem formulation is, right? We can introduce random variables, we can introduce chance constraints, and then this outer loop of risk allocation assigns those risk values. The turns into the deterministic planning problem, then we use our planning solver as a black box, right? So earlier what I did was I gave you a deterministic formulation of a kind of goal-directed model that you can throw, which can take a qualitative state plan, right? So I can just turn that into a chance constraint version, right, by introducing the capital delta, the risk capital, the random variables, do a risk allocation, and then call it a deterministic algorithm. So it's very easy and quick to implement that algorithm, right? It doesn't have the same kind of guarantees, right, that I gave you in the previous algorithm, but in order to get those guarantees, we had to reduce ourselves to a convex problem. Okay. So it's a very kind of quick way to implement the stochastic algorithm. And we okay. So that's kind of the basic idea. Now, in order to get to the qualitative state plan, then the things that I need to do will be to add in non-convex constraints, and then I need to add in temporal constraints. Okay? So I'll first go into the convex, right, and then I'll have run out of time for the break by then. Right? We'll then take a break, right, and then I'll have at most another half hour, and then the remaining hour and a half we'll look at temporal problems. Okay? Okay, so let's go to the non-convex case. Okay. So here we said that we now have regions that we want to be in, and we know how to deal with this, but we're now adding in regions that we want to avoid. These can either be constant throughout time, or they can be a function of time. So for example, in the case where we're controlling underwater vehicles, which we spent a fair amount of time with lately, then there's a shift, right, which is deploy those vehicles. That shift is going to be in different regions of time. We want to avoid that shift. So these obstacles are moving. There's no problem representing that. Okay, so it's really expressive. We just need to deal with convexity, and that corresponds to having a disjunction. So the key is, how do we deal with the disjunction, right, when we're dealing with this allocation? Okay, so remember before, right, we took a joint chance constraint, we distributed the probability within the conjunction, right? And that was our risk allocation, right? And then we determinized it. Okay? And that's how we got this formulation here. We're going to do something similar, right? Okay, so we're going to do a risk allocation we did before, but then rather than having a unary constraint, what we'll do is we'll have a constraint over a clause, right, or a disjunction. So somehow we have to deal with the disjunction. So we'll do risk allocation, and then the next step we'll do is something we call risk selection. Okay? And then we'll end up coming up with this formulation here. And what I just need to do is to kind of justify these equations. Okay? Okay. So as I said before, the first thing that we're going to do is that we're going to move the probability within these two conjunctions, right? And that's just a risk allocation step that we had before, right? We'll use Boole's inequality to simply say that the sum of the delta is less than delta, right? So this is simply saying that the probability that we violate all the disjuncts, right, has to be within delta. Okay? So, but given a disjunction, then we only have to satisfy one of those constraints. Okay? So what we'll do is we'll exploit the fact that if we have a disjunction and we want to say that the probability of A or B is within some bound, then we can come up with a conservative approximation by saying that the probability of A or B is satisfied if the probability of A is less than the probability of that disjunction and the probability of B is less than that disjunction. Okay? So what we'll simply do is to require that it is simply required that the probability of each of these disjuncts, right, is less than our lowercase delta, right, or equivalently the inverse of 1 minus delta. Okay, so if you look at it here, then the net effect is that we take the chance constraint, which is over the clause or the disjunction, and we simply move the chance constraint into each of the disjuncts. So we've simply said that each disjunct has to be bounded by 1 minus delta, because each satisfies the chance constraint, then the clause that satisfies the chance constraint as well. Okay, and that's, you get this equation here. Okay, so it's quite simple. So all we've done here is we've taken the same delta, right? Delta, and we moved that into the conjunction. And then once we've done that, then we have a unary chance constraint, and then we construct the safety margin. Okay, so just kind of remind the last couple of steps that I gave you, right? Which is, we looked at the case where we had a stochastic conjunctive program, right? It was a stochastic linear program, right? And that was fine. Then what we did was that we took the linear inequality constraints and we replaced them with disjunctive constraints, right? And that's what you call a disjunctive linear program. And so we said, how do we solve stochastic disjunctive linear programs? And so what we had said here is the first part of this is the same as before. So we do a risk allocation, but what we've now done is, rather than doing a risk allocation over inequality constraints, what we've done is we've done a risk allocation over a clause, which is just the disjunctive of linear inequalities, right? Okay. And then the way that we handled this were two ideas. The first one was risk selection, and that allowed us to bring the probability in within the disjunction, right? And then the second thing is to deal with the disjunction, we do a branch and bound search, and so we had to define a bounding function. Okay, so the point on the risk selection was that we have a disjunction. So it basically says that the probability of A or B has to be greater than 1 minus the maximum probability of failure. What we know is that the probability of the disjunction is bounded by the probability of each of the disjuncts, right? So using that, right, what we can do is we can move the probability within the disjunction by simply saying that we guarantee that one of these disjuncts, right, satisfies the risk bound, okay? And that's what we did here. And so that's how we got the formulation of the problem in terms of a deterministic formulation, right? But in order to deal with the clauses, we needed to do a branch and bound, and I was simply doing branch and bound over the clauses, right? And in doing the branch and bound, right, the main thing that you need to do is you need to define the bounding function, right? And I introduced the notion of fixed risk relaxation. And so the idea was that when we compute the bounding, we can do a relaxation by just getting rid of the disjunctive clauses. And that's a fairly common thing when you're solving disjunctive linear programs. The problem was still that if our bounding function is calling a convex optimization problem, then that can be too complicated. We don't really want an expensive bounding function. But the purpose of the bounding function is to compute a upper bound on the utility, right, or a lower bound on cost, right? So we want an upper bound on utility. So we can get greater utility by taking greater risk, right? So the idea is rather than satisfying your chance constraint, what we'll do is we'll take the extreme, right? So our relaxation is to say that whatever global risk that we're allowed to take, capital delta, we assume that we can take that at every point in time, right? And so that corresponded to the relaxation that I gave you earlier, right? Which is that every constraint is allowed to take the full risk, right? So certainly the sum of those deltas, right, is not going to be capital delta. It's going to be capital delta times n, where n is the number of constraints that we have. So it's going to be taking, much to risk, right? But that will give us a bound, an upper bound on utility. And because the lowercase delta has become a capital delta, right, it's become a constant, right? We can then plug in that constant, and then we have a linear program that we can solve. We can solve that very quickly. Okay, so that's what we do in this algorithm, right? So that's where the intuition in the fixed risk relaxation is that we take much greater risk than we're allowed, because we're allowed to take capital delta risk at every point in time with respect to every constraint. Okay? And so then that gave you basically, here were the two different original stochastic formulations, the conjunctive and the disjunctive case. And here's the reformulation of these as deterministic problems, right? The first one being a convex deterministic program, the second being a convex disjunctive deterministic program, right? Okay, so if you look at how it then performs, so hopefully we'll get this to work. So in this case, we go back to the firefighting scenario. And remember, the problem in this case is that we want to be able to have the fire out, right, at the two locations where I don't quite see where the fires are, but when we run the movie, we'll see it. That involves moving and collecting water, putting out the fire, avoiding the obstacles, and we give the linearized dynamics of the vehicles to fly. So at the upper level, we'll be doing an activity planning, which is just a classic PDDL generative planning, but we have a series of goals along the way. And then at the lower level, right, to move between different locations, then we frame it as a model predictive control problem. Because we have areas we want to avoid and regions that we want to go to, then it is a non-convex problem. And so we use the algorithm that I gave you here, or a variant, a more recent variant of that algorithm. So this is a dramatically sped up simulation, right? But so it's planning, moving along the way. It's constantly kind of planning over a horizon, right? And then doing the update. Okay. And it is the case that this, that these algorithms now scale well enough that you can do this in real time, right? So the original algorithms using the particle sampling based approach, we could deal with one dimension over time. At this point, we can deal with much higher dimensional problems, projected over time, and it does perform reasonably in real time. Okay? Sure.
At the beginning of the tutorial, you were talking about something where the resulting problem was like a mixed integer linear program or something, and here we have and so you're talking about doing this in real time, and like we have bounds on solving time for.
Well, so the next couple of slides, I'll show you some of the things in terms of performance, right? I mean, so there's two different things you said. So
empirical argument, or like
in terms of the runtime, it's an empirical argument. I mean, it's at the point that it either becomes a mixed integer linear program or a disjunct linear program, then there's not that much you can say in terms of the worst case runtime, right? Okay. It is the case that you can have more anytime properties in terms of deciding the horizon that you plan over. So you do have that flexibility to adapt, right? But there's no worst case guarantees. There are other questions that you can ask in terms of in a finite horizon case, right? Then what guarantee can you have of the risk over the whole horizon, right? So we've done work where, so that's not the runtime, but it is the guarantee in terms of success, right? So I'll answer the question that we do know a bit unanswered than the one that you don't. So there's things we can say about that. You could ask about that later. But in terms of the runtime, right, not the guarantee. The thing that we have tried to do is to simply, it is the case in the first thing that I gave you, right, where it is a convex problem, right, then we can guarantee optimality, right, modulo Boolean inequality, but we can't guarantee runtime.
And all these cool applications that you've been working on, are the clients typically happy with that sort of guarantee, saying like, oh, I can give you any time and we'll adapt, and if they're okay with that?
Well, I mean, you're kind of pushing it along the way. I mean, at one level, since they've been using model predictive control, right, using a deterministic formulation, then they're used to the fact that they're doing a finite horizon, right? So they don't have a problem with that, right? I mean, there's always the adoption of those techniques is really, several decades beyond when the techniques become boring, right? Okay, so they're used to that framework, right? They've been dealing with algorithms that deal with uncertainty and using heuristics. For example, we do stuff in unit assignment for power assignment, right, or power restoration. And what they do is they use heuristics like guarantee that it can handle single points of failure. So they're not doing a probabilistic formulation at all, right? There's work that we're doing on a microgrid right now, and the problem is that they've said use these. So the risk problem kind of relates to what Erez is doing, right, which is going to be deciding what times do we allow people to use power. Right, so we turn on and off outlets in India, right, in these small villages that don't have power. The problem there is it needs to be able to run in a processor which costs $2. Right, so they're not happy at all about the performance, and we're trying to figure out much more efficient ways to do it. So you always really want to speed these things up more, but I mean, I can tell you some of the other stuff we did on this cruise and kind of what the insight was there. I mean, part of it is the state of the art is it doesn't really deal with uncertainty. Right, so even crude approximations of these things, you don't have to solve it exactly. You have to do better than the current practice where it doesn't think about risk at all. Right? Wait, does that make sense? Dave?
Yeah, so at the high level planning, you're deciding to go from the hangar to the fire to the lake, back to the hangar and so on.
Right.
Now, at the lower level, in doing path planning, are you only planning for those individual segments separately, or is the receding horizon actually crossing the boundaries where, between where you're getting to the lake and going back to the hangar?
Right, so in the case, for example, of PSULU, which is the algorithm we're showing here, then yes, it's taking the temporal plan which has several activities, temporal constraints and state constraints, and it's planning for that whole thing. The thing will be, so Sulu will do that. It is the case that that because it can't operate in real time and deal with the full horizon, right? If you require it to be dynamically planning and doing a partial horizon, what it will do is it'll pick the initial part of the plan, right? And then it has to compute some abstraction beyond that horizon. So the original Sulu spent a fair amount of time being clever about kind of identifying what the relevant constraints are and trying to fold them into the heuristic. Stuff that we've been dealing with more recently has been kind of dealing with some of the issues, right, that Wheeler dealt with in terms of not taking too much risk in terms of the discrete time formulation, and we focus less about kind of the full plan, full horizon. But the original formulation I gave you was encoding the full plan as a constraint, and then you need to satisfy it. And a number of applications we'll deal with is that we are planning at a smaller update rate where we're planning actually over the whole horizon. But the open technical issue is in those cases where you're doing a finite horizon planning, right, then how can you be smarter in the trajectory optimization about what your heuristic is? Does that make sense to you?
Yeah. Now, is it ever the case that when you do the planning at the lower level, it turns out you can't meet the risk criteria, and therefore you end up having to go back up and plan, find the
Yeah, so you'd have that, right? Okay. Now, there's a lot of different kind of variants you do this depending on your funder or something like that. Independent of whether or not there's a higher level planner, right? So we've been doing a lot of travel planning problems and stuff like that where people are giving you requirements. Now, actually, in the demo, if I get to it, you'll see it in a moment, where in this case, you actually go back to the operator, right? And then you have to go through a negotiation with the operator to relax constraints. In the case where you have a general planner, the thing that we'll do is when it becomes inconsistent, then you want to be able to extract a conflict or a no-go, right? Which summarizes why it was too risky, and then the general planner uses that as guidance. But whenever we're interacting between an activity planner, right, and some other routine such as trajectory optimization, we're always extracting a no-good of some form. Okay. In the case where we deal with the user, then what we do is we propose relaxations, right? So we say we propose to the user, are you willing to take a little bit more risk here, or are you willing to take a longer time here? That's the other idea. Okay. So I'm going to kind of go through one more step really quickly, and then I'll try to show you a little bit of the empirical results. It's not it's thorough, right? Okay. So the last thing to do is that in this case we have convex and non-convex constraints, and we could assign these for particular points in time. The thing is, our original formulation left temporal flexibility in terms of when these episodes start and end, right? And those are expressed as a set of simple temporal constraints, right? So one simple way to deal with that, right, is to introduce these temporal constraints as an additional set of temporal constraints. And then, so just as we solved this problem, right, by basically reducing it to a series of these problems and using the previous algorithm that we had before, one approach we can deal with temporal constraints is to do a branch and bound approach where we search over the set of possible schedules. And then for a particular schedule, right, what we do is we use these two algorithms to try to compute the optimal trajectory, and we can do a bounding and the likes. So that's one algorithm we've done. What Erez will talk about is going to be much more sophisticated in terms of the temporal problems, but I just want to complete this as a simple story. So there's a version of the problem. I'll show you a demo in just a moment, where just the outer loop is basically doing a branch and bound search over possible schedules, and then finding a trajectory given that schedule. Okay? And then we'll see how that performs in just a minute. Before I show the performance, let me just show you kind of an integrated system that does this. A number of you have seen this. So sorry for showing it again, but it will kind of show the integrated system. In this case, we have an activity planner, right, which operates on top of trajectory optimization. It does have the temporal constraints, right, where the firefighting example that I gave you didn't include temporal constraints, right? And it does involve user interaction to deal with oversubscription. This does have audio, so we'll see if you can hear this at all.
I want to go to the bowling company.
Any more preferences?
I want to be there in 3 minutes.
Anything else?
I want to stop at Leisureland.
Any other requirements?
No.
We cannot get there in 3 minutes, but we can get there in 6 minutes.
That's fine.
Okay. I have a valid plan. There is a change in the weather conditions. I will replan the pass.
Okay, so in this case, it is taking, there's a higher level activity planner which has contingent kind of landing points and the likes. It comes up with the temporal plan, which is a quality of state plan, and then
The
the
current
algorithm
destination is unavailable.
generate a trajectory.
Diverting to the preferred alternate landing site, Harvey Field.
In this case, the risk that it's dealing with is twofold. One is that there's a weather system, and it's a moving weather system, right? There is a level of risk of turbulence, right? And so based on how the user specifies what risk they want to take of getting too much turbulence, the algorithm decides how far to stay from that moving system. Because the system is moving, you don't know exactly what rate it's moving. That's why you want to do the model predictive control. You are trading off the probability of flying through the weather system versus not arriving at your destination in time. So that kind of highlights the coupling between temporal constraints, right, and state constraints. Now, if you look a little bit about the performance, right? Now, these are just kind of a set of selected runs as opposed to a very, a very thorough set of benchmarks. You get a more thorough set of benchmarks, right, in the temporal problems, right? So in this case, right, we had the constraints, right, of remaining in a set of region, in avoiding, right, the unsafe region while achieving your destination goals. We had risk associated with each of these. And what this algorithm will do is it'll show you where it spent its risk, right? So it basically decided to spend some risk in terms of where it arrived at the scenic region here and the point at which it left the scenic region, right? So it might have arrived a little bit too late, or it might have arrived so that it just was outside of that region, or it may have left just a little bit too early. So those are the two places where it took risk. And then it took risk again. Well, I think it's mainly those two, right? So it's these two. I think the last one is in terms of arriving at its destination, right, in time. The other chance constraint was remaining safe, and here's the risk allocation that it took here, and that risk allocation corresponded to clipping the corners, right? Okay. So that's what the results you'll get. If you look at the runtime for this problem, right, then we're taking a few seconds to generate this solution, right? And this is about, the time horizon, about 16 time steps, right? That's kind of the typical horizon for a model predictive control. If you increase the complexity of the problem, right, by not too much, then it becomes much more difficult, right? So in this case, we have this series of 4 goals along the way. We have 2 obstacles, right? The state space is the same, right? But if you look at the compute time, right, then it's taking 2 hours, right, to solve this problem, right? So that's the case where the techniques are still not up to the kind of performance that you want, though we are dealing with multi-dimensional problems. So the way that we address this, right, is that the main cost is the number of linear programs that we need to solve along the way, right? And so what we want to do is to reduce the cost of solving the linear programs. There's a whole range of techniques you can explore. The particular technique that Hiro, who did this thesis on it, this was a collaboration with Roy and Banerjee. Then they've developed a technique called Boost LP. What it does is it's a learning technique which will learn, right, a bound, right, on the solution to an LP. There's a number of techniques that deal with this. So parametric LPs is a way to kind of pre-compile the set of the family of solutions to an LP. The nice thing about the Boost LP, which is kind of a learning algorithm along the way, is that it's guaranteed to compute a bound on the solution to that LP. So in terms of a branch and bound, it's quite helpful in terms of providing an admissible heuristic. So if you look at the performance, right, for these kinds of problems, right, as a function of the number of obstacles, the number of waypoints, right, then we're already getting a dramatic speed up. So we are getting back to kind of the level of performance that you'd like. But the issues of trying to achieve kind of solid performance over a broad set of problems is still very much an open problem. Okay, so that kind of gives you some sense of the performance on those examples. Now we're doing a much more thorough investigation, but those are things that we're not kind of ready to publish yet. Here's just another kind of practical demonstration. Is it starting? So a concept that NASA's explored a lot is a spherical spacecraft, right? So at NASA Ames, there was a personal satellite assistant, which is a spacecraft that would run an International Space Station. MIT students developed a similar kind of concept called spheres, which is now also being managed out of NASA Ames. And that also kind of operates within the International Space Station. And you can use that for a testbed to do rendezvous and docking and similar procedures. So this is an example where we're simply using PSULU to basically give it the goals of going into a hold position and then moving and docking within a period of time. And the algorithm works fairly effectively. This is a 2-dimensional test bed, and then what you do is you do the demonstration on the 2D test bed, and then you go to International Space Station, and you demonstrate it International Space Station as well. So those are just some of the practical demonstrations of it. So a number of those are kind of things that we did about, maybe about 6 or so years ago. We did go back to sea about 2 months ago, right? And so we, in this case, rather than controlling an autonomous vehicle which is propelled, which is similar to what we did about 7 years ago, instead what we did do was to control of much cheaper vehicles. So this is a vehicle called a glider, which is more like a $60,000 vehicle. And the thing about this vehicle is that it has no propeller. It only uses buoyancy to kind of move up and down. It is much more subject to the currents of the environment. But the nice thing about these vehicles is you can send them off for a month or longer, right? Where a propelled vehicle, you usually send it out for 8 to 20 hours, right? The other thing that's nice is although we're using a crane here to deploy this vehicle, right? You can also just have 2 people and pick up the vehicle and toss, and kind of most of the time we spent going into a dinghy and kind of tossing into the water. So the interesting thing here is that if you look at how we do ocean exploration, then the first thing that people would do is they'd have a cruise, like a ship like this. They would hang some instruments off the side of the ship, and you get a very little amount of data about the ocean. Autonomous vehicles like this means that you can go off and send them off, but one of those ships typically has only one of these vehicles and then one remotely operated vehicle, a crew of about 20, maybe about 14 scientists. So it's kind of like NASA's concept of Cassini or Galileo, right? You had this big, what would be called a Battlestar Galactica instrument to collect data. And the thing is that this cruise costs $50,000 a day. So that's $50,000 to control this one vehicle. In the demonstration that we did about a month and a half ago, we took 7 different vehicles of all different types. So here's an underwater glider. Here's something called a wave glider, which would go on the surface. It has basically the upper part has a, it looks like a surfboard with solar panels. This thing goes 80 foot below, and basically it uses the wave motion to move forward. This vehicle has gone from the west coast of the US to Hawaii and back, right, kind of fully autonomously. And you could send these things off for years. We also use propelled vehicles called Erez, and all these are about $60,000 to $100,000. If you can use these, then you can have a dozen or so vehicles operating around the ship at the same time, or they're sufficiently small that you can just try to get the ship out of the picture. So that really produces a paradigm shift in terms of ocean exploration. The challenge is mission planning, that there's a lot of these vehicles operating at the same time, and you have to deal with that. And then you have to deal with the uncertainty. Okay? So the uncertainty in particular is that once we added all these vehicles operating at the same time, then they started kind of colliding into each other. So let me just say a little bit more about this, right, before we kind of wrap up. So if you look at this particular vehicle, right, called a slocum glider, the way that it works is it was an evolution of a concept of a buoy. The way that buoys, right, that just kind of operate in the ocean currents is that they adjust buoyancy. So they move up and down the water column by adjusting buoyancy, right? So they become more buoyant or less buoyant, and they just can move up and down. So the idea is that we could actually move if we just put wings on the buoy, right? And then we put a weight which tips the nose of the buoy kind of down or up. So the way that the vehicle works is that you move a weight to the front of the vehicle, and then you reduce the buoyancy, and then it goes down, and then it glides right on its wings. And then when you get down to the maximum depth, right, then you shift the weight back, you increase buoyancy, then you move up. So it just kind of yo-yos up, and it consumes energy only at the turns, right? So that's why it's very efficient, but it's very subject to the currents. So the way they deal with this is that normally you operate just out in the middle of the ocean, right, where it's very safe, but the problem is the middle of the ocean is a lot less interesting than near the shore or at reefs. So the challenge was, could you operate these gliders within reef areas? So this is Scott Reef, where we spent 2 weeks. And so the challenge was, could you take this vehicle and could you treat the reef as an obstacle course, and could you come up with a course of moving the vehicle in and out of these different obstacles while having it work safely? And so what we did do was to show that you could do activity planning. And in this case, it wasn't generative activity planning. It was more of a kind of multi-vehicle routing with time window kind of problem, together with trajectory optimization, kind of the 2 main techniques we talked about here. And using those techniques, you could effectively control this vehicle and much more effectively than how people traditionally do this. What we also learned is that a lot of these vehicles were starting to kind of collide into each other each day, right? So for example, the Falcor ship almost ran over the slocum glider because it thinks that vehicles are down and they're never on the surface, and this thing's yo-yoing between the surface and going down. We have pictures from this kind of photo float, which was drifting around. If I had had time to show you how it was moving closer and closer to the Falcor propeller until it almost got chopped up. There's another one where one of the propelled vehicles called the Ivor was being chased by a shark and the likes, right? So the problem with the multi-vehicle coordination is an essential one. But if you do that, then what we'll see is that people will stop doing one autonomous vehicle, which costs us $1 million on a cruise, and then they'll start shifting to doing lots of vehicles. But risk is, and mission planning is kind of an enabler for it. Okay, so then just kind of wrap up, and then we'll kind of transition to Erez segment, right? So in this case, we've been just kind of talking about mission level planning and trajectory optimization. You can then talk about trying to do this where you're controlling multiple vehicles, where you don't necessarily want to solve this in a centralized manner. But for example, you're doing cooperative vehicle coordination, where you have to be able to deal with the risk of vehicles colliding together. So there's multivariant versions of these algorithms. In this case, you can use techniques such as a dual decomposition to try to decompose this into a set of trajectory optimization problems for each vehicle and then coordination between them. If you're doing a dual decomposition, then that kind of has a nice kind of market-based metaphor where what you're doing is that you're basically setting up an auction between the sub-problems. In this case, what you're doing is you're auctioning off risk. So what you're doing is that you're setting the price. What you're doing is you're setting the price of risk. You're then having the algorithm solve each sub-problem based on the price of risk, and then you iterate until demand for risk meets supply. Okay. Okay. So then just to wrap up. Okay. So the central idea, right, has been the idea of we're going to distribute global risk, right, to the individual constraints as a risk allocation process, right, and we're going to increasingly come up with better risk allocations which provide higher utility, right, that we've looked at the formulation of this problem first for convex problems, then non-convex problems, and I've touched briefly on temporal problems, which is Erez is going to talk about next. There's a whole line of work on doing kind of distributed versions of these algorithms, which we're not including in this tutorial. If you look at the solution techniques, right, then the problem formulation are basically different variants of stochastic optimization problems which have chance constraints, right? And the main techniques that we've introduced for this are either to do a single convex optimization problem which has the decision variables on risk together with the control variables involved, or we do an iterative risk allocation, and we've kind of shown how you can generalize those to increasingly expressive problems, right? And the kind of the main takeaways then is that it's important to not just think about maximizing utility where you have risk folded in, but to talk about maximizing utility within bounded risk. And the idea of risk allocation is one idea to do that. Okay? So with that, I'll take, do we have any kind of additional questions at this point? Okay, good. So what we're going to do is we're going to forget about state variables, right? In trajectory optimization, we're going to deal with just temporal problems, though so we'll start with simple temporal problems, right? We are going to talk about a stochastic formulation of the temporal problem. We are also going to talk about a reformulation, right, to a deterministic problem, since or to a set bounded problem. And since this community has done a lot of work on STNUs, and we're going to leverage the tools on STNUs. So just kind of one quick question, right, which is how many of you kind of know about simple temporal networks under uncertainty and methods for solving those? And how many of you have just never heard of them before? Okay, so Erez will keep that in mind.
All right. So here's the thing, right? Time is very critical. So this is, what is this, Cassini? I don't actually know what this is, but this is my favorite example. So this is a Venus lander. Venus, if you haven't heard, has a very, very toxic atmosphere, and if you send anything there, it'll die in a matter of hours. And so you really want to make the most of the time you have on Venus. And that's where managing time comes in, right? And so what I'm going to be talking about today is scheduling with uncertain durations and bounded risk. Okay, so again, putting this in context, we have some generative planner, and it's got some risk-bounded and trajectory planner, which Brian just told you about. And it also has to do risk-bounded scheduling, which is this part of the talk. The way this tutorial is structured is, first I'm going to introduce simple temporal networks and what feasibility means in that context. Then I'm going to talk about set-bounded uncontrollable durations with strong and dynamic controllability. And if you know this, then you can kind of snooze now. Then I'm going to switch to talking about simple temporal networks with probabilistic durations and how you do chance-constrained scheduling. So if you haven't heard of Doctor Who. He's weird. And right, basically time is a ball of wibbly wobbly, timey wimey stuff. Because we're not actually going to be thinking about time. We're going to be just thinking about variables and constraints. Now, the variables are going to represent time points, and the constraints are going to be temporal constraints, but we're going to forget about that for most of the time. So this is something we discovered the hard way when we gave a course. People don't know that temporal means time. So temporal is time, okay? And temporal problems are basically used when you have some deadlines you need to meet, or when you have some coordination constraints, like two agents that need to meet right at a specified time, for example. So we're going to introduce simple temporal networks with this example of a rescue scenario in a volcano. So there's this group of hikers, and they're climbing a volcano for some reason, and the volcano erupts. And so we need to get this first aid kit from the depot to the hikers. And we're going to do that using two quadcopters that are doing a relay thing. So the first one is going to pick up the package at the depot and deliver it to the base station. And then I guess it runs out of batteries or whatever. And then the second one is going to pick up the first aid kit at the base station and take it to the hikers. Okay? So this is our scenario. And of course, we want to get the first aid kit there in time, right? Because there's a volcano coming down, and I guess the first aid kit is what's going to save them. But anyway, so we've got two quadcopters, right? Q1 and Q2. So Q1 goes from the depot to base station, Q2 from the base station to the hikers. So let's assume that the volcano erupts at time 0, which is the start of time for all we know. And the hikers need the med kit in at most 20 minutes. Okay? So going from the depot to the base station takes between 2 and 3 minutes. Going from the base station to the hikers takes between 14 and 16 minutes. Transferring the med kit at the base takes at least 1 minute. Okay? Now, first of all, one important thing to note is when I say between, for now we're assuming that we can choose how long it's going to take. Okay, so this is what's called a controllable duration. So let me ask you guys, do you think this is feasible? Can we make it in time? Yes. Let's have a vote. Who thinks yes? All right. Who thinks no? All right, cool. Now, what if I add another constraint that says that quadcopter 2 needs to charge for at least 15 minutes before it can go to the hikers? And of course, it can only start at time 0, okay? So who thinks this is feasible now? No. Yes? Who thinks it's not? All right. So it's not, but it's kind of hard to see it this way, right? Which is why we convert this to a more graphical notation, and we can run algorithms on a graph that will tell us when to do stuff, basically. So we take this example without the last constraint I added, and we can create this thing, which is a simple temporal network. Okay, so start of day is S, which is a time point or a variable or whatever you want to call it, right? D is when the first quadcopter reaches the base station. T is when they finish transferring, and F is when they reach the hikers. And we can encode these temporal constraints as basically labels on edges, right? So going from depot to base station takes between 2 and 3 minutes. Transferring takes at least 1 minute, so it's between 1 and infinity, right? This is between 14 and 16. And the first aid kit needs to get there in between 0 and 20 minutes, okay? And what this is actually hiding is just a bunch of simple temporal constraints, which are basically very simple cases of linear constraints. So these are called difference constraints, right? So D minus S is between 2 and 3, which is this, right? T minus D is more than 1. F minus T is between 14 and 16, and S minus F is between 0 and 20. Okay, so basically each edge here encodes an upper and lower bound on the difference between the two time points that it's connecting. And so this is actually a formulation that came from Rena Decter, who is probably around here somewhere. So I hope I get it right. Now, what is a solution to a simple temporal network, right? What we want is basically a schedule, which is an assignment to all event times or variables, right? So this is one possible schedule solution, right? If we set t equals 0, d equals 2, sorry, s equals 0, d equals 2, t equals 4, and f equals 19, right? It's going to satisfy these constraints, or it's going to give us a feasible schedule, right? That's going to satisfy this, because these are really the same thing in different notations. All right. So a more formal description, right? A simple temporal network consists of a set of time point variables, which are called n, set of simple temporal constraints, which are called e, and these simple temporal constraints look like this, right? x1 minus x2 is between lower bound and upper bound. So x1 and x2 are the nodes, and lower bound and upper bound are real numbers or plus or minus infinity. And an STN is consistent or feasible if there's an assignment that satisfies all the constraints. Okay? Right. So now let's look at the STN, which has the additional constraint that Q2 needs to charge for at least 15 minutes, right? So this is this arc, this edge, which is added, right? This is 15 infinity. And we said this is not feasible, right? How can we see this in the graph? So we can look at these three edges, right? So what did these say? T must be at least 15 minutes after S, and F must be at least 14 minutes after T, right? So this is at least 29. But this says that it's got to be at most 20, which is why it's inconsistent. Okay? So this is called, so this means that there's no way to satisfy these simple temporal constraints, right? Now, how do we actually find this, right? I showed you where the problem was, the conflict. But the way we find them is we do this weird thing, which is called the transformation to a distance graph representation. Now, basically what I'm doing here is I'm taking this edge, right, 2, 3, converting it into 3 here, and minus 2 here, right? Taking this 14, 16, converting it to 16 here, and minus 14 here, right? So 1 infinity converts to infinity, which is nothing, right? And then minus 1. Now, an easier way to understand this is you basically take something that looks like this, right? D minus S is between 2 and 3. And you want to convert it to a form that only has less than. So D minus S is less than 3. And then in order to get the 2, you kind of multiply by minus 1, and you get S minus D is less than minus 2, right? Which is equivalent to D minus S is greater than 2. But we just draw these constraints as a graph, okay? So to go from D to S is at least 3, right? And to go from S to D is at least minus 2. Sorry, at most minus 2, right? Now, the conflict in the STN corresponds to a negative cycle in the distance graph representation, right? So now it's much easier to see not only which temporal constraints are responsible for the thing being infeasible, but actually if it's the upper or lower bound on each of these, right? So we can see that it's the 20 here, right, the upper bound, plus the 14 and the 15, right, which are the lower bounds of these. Okay? So in order to check whether an STN is consistent, right, we can do the transformation to distance graph. Then we can check if there's a negative cycle in the distance graph. If there's a negative cycle, that means that the simple temporal network is inconsistent and there's no schedule. If it doesn't have a negative cycle, then it is consistent and we can find a schedule. And if you want the proof, well, you can ask Rena. I won't give it. Now the question is how you actually find a negative cycle when you have negative edge weights, right? It's not trivial, but there are existing algorithms that do that. And most of them build an all-pair shortest path matrix for the distances between all the nodes. And then if that matrix has a minus infinity entry, then that means they're in a negative cycle. This APSP thing is also good when you're actually trying to find a schedule, right? It's going to give you dispatch windows for each event. And so this is going to take basically n cubic time. And in practice, we can actually exploit the structure of the SDN and get this running faster empirically. All right. So any questions about SDNs so far? Okay, good. So now let's move on to simple temporal networks with uncertainty. So as I said before, right, we assume that we can control all of the durations, right? So when we say that quadcopter 2 can go from the base station to the hikers in 14 to 16 minutes, I'm always going to choose 14, right? I mean, why would I ever do more than what I need, or the minimum, right? At least for this problem. But you know, this is not often the case, right? And especially, and I can tell you this from experience, when you're trying to execute actions on robots in the real world, you really have no control on how long things take. You're kind of hoping it actually works, and if it works, you're hoping it's fast. But when you're calling, let's say, a randomized motion planner, you really have no idea how long the thing will take. So in 1999, which is a really long time ago, Vidal and Farguet introduced the notion of simple temporal networks with uncertainty. And that incorporates a set-bounded notion of uncertainty. So the idea is that, let's say, going from Jerusalem to Tel Aviv is going to take between 45 to 120 minutes, okay, depending on traffic. Now, I have no control on how long this is going to take, right? But what I do know, what I have is basically a promise from nature that it's never going to take more than 120 minutes, and it's never going to take less than 45 minutes. Okay, so the duration is always going to be somewhere in that range. Okay? And this is the notion of set-bounded uncertainty. And it's so that's got a parallel to the robust control that Brian described, right? The circle. It's going to be somewhere in the circle. So, for example, right, we have two rovers that need to search locations 1 and 3 or 2 and 4, and then they need to meet at location 5, right? So the durations, so the duration of searching at location 4 and searching at location 3 are uncontrollable. So this square thing denotes what's called a contingent time point, which is basically just the end of an uncontrollable duration. So the idea is that for events or time points that are marked with circles, I can control when they happen. I can dispatch them, right? For squares, these are the ends of uncontrollable durations, and I can't control them. I can only receive them. So they're called receive time points or contingent time points. And so, for example, if I start searching at location 3 at time 5, right, then the end is going to be somewhere between 7 and 11, right? That worked out nice. But I don't actually know when. Okay, so an STNU, right, looks very similar to an STN. It's got a set of variables representing time points with real value domain, and it's got binary constraints of the form xk minus x1 is in upper bound, lower bound. Okay, but with STNUs, some of these are marked as contingent links, and the others are requirement links. And so the idea is that contingent links correspond to uncontrollable durations, right? And they have this square notation, and these are the constraints. So we can control how long this is going to take, right? We can't control how long this is going to take. Okay? Is that clear? All right. So an STNU, right, is basically a set of time points, edges, upper bound, lower bounds, and requirement links and contingent links. So we're going to assume that uncontrollable durations have a minimum duration of at least 0, because otherwise it doesn't really make sense. Okay. So when you look at an STNU, right, you can kind of think of the notion of a projection of an STNU to an STN. So in this example, we have one uncontrollable duration, right, between C and D, which is going to take somewhere between 2 and 4 seconds, right? So for any realization of the uncontrollable durations, we get something which is basically an STN, right? So if this takes 2, we get an STN that looks like this, right? If this takes 3, we get an STN that looks like this. If this takes 4, we get an STN that looks like this. Of course, it can also take, 2.739, whatever, right? It doesn't have to be integers, but we have to think about all of the possible realizations of all the uncontrollable durations. Now, when we're talking about STNUs, we can no longer just ask whether the STNU is feasible, right? So the question of STN feasibility was, can we come up with a schedule? But in this case, obviously, we can't come up with a schedule because there are some time points that we can't schedule. We're not allowed to, right? So there's, there's 3 different notions of what's called controllability, okay? So the first one is strong controllability, which means that I want to come up with a single schedule for the executable time points, okay? So the time points that I can control, which ensures that no matter what realization of the uncontrollable duration happens, the schedule is still going to be consistent. Okay, so I'm coming up with one schedule a priori, right? And it's going to work for everything. Okay? The other notion is the notion of dynamic controllability, which says that basically I'm going to make decisions on the fly, right? So I can observe how long some uncontrollable duration happened, and based on that observation, I can adjust my schedule for future events. Okay, so obviously this is a weaker requirement, right? So if every strong schedule is also a dynamic schedule, right? You just don't change your decisions. So this is more applicable, but this also requires coordination. Okay, so for example, if I have a set of AUVs, right, swimming around the ocean, and if they need to coordinate, then they need to communicate. And I don't know if you noticed, but communicating underwater is really, really difficult. I think if they get like 9,600 baud, they're happy, if it works. So finally, there's the notion of weak controllability. Nobody really cares about weak controllability, but they defined it, so we kind of have to, at least mention it. And sorry? No, I don't? All right. Well, I'm just going to say that basically it's the idea that for every realization, there is a schedule, right? It doesn't have to be the same schedule. So kind of, if I know all of the realizations in advance, I can come up with a schedule. It's not really useful for anything except for kind of pruning things, right? So if something is not weakly controllable, then it's obviously not going to be strong or dynamic controllable either. Right. So today we're going to focus on strong controllability. And if you want to learn a bit more about dynamic controllability, actually Jing has a talk. When is it? Tuesday? Wednesday? Wednesday, yeah. But so this tutorial is going to stick to strong controllability. Right. So what we want to do now, right, is find a schedule for the executable time points, right, the ones I can control, that is consistent with every possible outcome of the uncontrollable durations, and I want to generate that offline so that I don't have to do anything while the thing is executed. So let's look at this very simple example, right? So we have begin search, right, and we have arrive at location 2. So this is going to take between 1 and 2, and it's uncontrollable. This is going to take between 2 and 6. This is going to take between 2 and 3. And we're going to call these durations A, B, and C. Okay? So let's see what schedules might be strongly controllable. Okay? So let's say we begin at 0, right? And let's say we schedule this at time 4, okay? So this is going to be consistent for a equals 1, right? Because if a equals 1, then we can make this take 3, right? And if a equals 2, then this can take 2. So if we schedule this at time 4, then we're fine, right? If we schedule this at time 3, we have a problem, right? Because if this takes 2, actually if this takes more than 1, then this is not going to be met, right? This constraint is not going to be met because, so this is not going to work, right? Because this is going to be 2 plus at least 2. So this is going to happen at 3, right? So this is not a valid schedule. Okay, but if I schedule arrive at time 4, then I'm happy. So that's an example of a strong schedule, right? And I don't need to schedule this, right? Because I can't. I wish I could. Okay. So how can I check strong controllability? So basically what I'm going to do, and this is also from the Vidal and Fargia paper I mentioned, is I'm going to take my uncontrollable durations, right? And I'm going to make sure that I restrict the requirement links, okay, the controllable durations basically. So I'm going to restrict AC in this example so that it doesn't squeeze AB, okay? So when I'm finding a schedule, right, when I find a time window when I can execute one time point, it restricts the time points that are connected to it, right? And in this case, I can't restrict B. I have to leave all of the original space for B, okay? So instead I'm gonna restrict AC, which is controllable, so that the constraints on AB are always gonna be met. So let's see how this works. And I should mention that this is the distance graph and not the STNU, right? Remember, so this is upper bound, lower bound, right? Upper bound, lower bound. All right. So basically, there are 4 types of edges in an STNU, right? According to the type of time point that they're connecting. So it's either executable, executable, executable contingent, contingent executable, or contingent contingent, okay? And for each of these, we'll have a slightly different treatment. So if I have something that looks like this, right? I have an uncontrollable duration, right, between A and B, and I have a constraint from C to A, right? So this is basically A minus C is less than A, right? Or I can have a constraint from C to B, or I can have a constraint from B to C, or I can have something like this, right? 2 uncontrollable durations with a constraint between the endpoints, so contingent, contingent. So if I have an edge which is executable, executable, then it's basically just a simple temporal constraint, and I don't have to do anything with it, right? So what I want to say is DCA, right? This distance is less than A, okay? Now, if I have if I have a constraint from C to B, right, then I want to avoid squeezing this, okay? So what are the possible cycles here, right? It's going to be DCA plus UAB, the upper bound here, right, and B. So I want to make sure that I don't squeeze this, okay? And so I'm going to add a constraint which says DCA plus the worst case thing that can happen, right? And in this case, the worst case is this taking the longest, right? So if this takes the longest, then it's going to affect this, right? So I'm going to make sure to add the constraint DCA plus the upper bound on AB is less than B, okay? And I can just move things around, and I narrow the constraint here on DCA, right? So now it's going to be DCA is less than B minus UAB, okay? So instead of adding this constraint, right, between an executable time point and a contingent time point, right, instead I add a constraint between two executable time points, right? But that constraint is affected by this uncontrollable duration. Okay? Is that clear? Right. So the other case is, right, and then I just update that. Okay. Now the other case is the other way, right? So I have a constraint going from B to C instead of from C to B, and actually, if I just flip the sign here, I can flip the direction and do the same thing, right? So I mean, basically, what this does is the same thing. It's symmetric, right? It just updates CA to or AC to DAC is less than C plus the lower bound, right? Because now we care about the lower bound. But it's really the same reasoning going on. Okay. And finally, in this case, right? Then, well, we have kind of this possible cycle, and we can update this to DCA is less than D minus UAB plus LCD, which is going to look like this. Now, you can really think of this as applying the two previous transformations, right? So first we do this, right? The first rule, and then we do this, the second rule, and it's equivalent, okay? So the details of this aren't super important, right? What I do want you to understand is that I can encode strong controllability checking as basically feasibility checking of an STN, right? Which I obtain by avoiding squeezing the uncontrollable durations. Okay, so basically I still end up with an STN that I need to check for feasibility as before. Okay. So everything clear so far? All right. So now if you knew about STNs and STNUs, you can wake up now because we're going to switch to probabilistic simple temporal networks. And we're going to do two different approaches for solving these. So constrained risk allocation and then iterative risk allocation. So now we're going to switch to a different example, which you might recognize. It's from Star Wars. And it's the assault on the second Death Star, I believe. So, right, we have our start time point, and then our fleet is going to hyper jump to the Death Star, and then it's going to jump and then attack. And before it can attack, we need the ground assault team to disable the shield generator on the forest moon of Endor. Okay, y'all remember that? So the shields have to be down before the fleet arrives, right? Because otherwise they're all going to die. And then, of course, things take time, right? So this is going to take 6 hours. This is going to take 3 hours. The ground assault is going to take between 4 and 6 hours. They can only attack after the fleet arrives, right? Because otherwise they're not there. And again, these are uncontrollable durations, right? So the ground assault is going to take between 4 and 6 hours, which I can control, and the fleet hyper jump is going to take between 6 and 12 hours. Let's see if there's sound. Right, and in this case, yes. Okay, so so this is our STNU, right? But the thing is, who is actually who can tell me that the ground assault is going to take at most 6 hours, right? That's right. Nature is going to guarantee that the ground assault is going to take at most 6 hours. That's not very realistic, right? I mean, who knows, right? So really, when we're talking about STNUs, right, we assume that the set bound covers some reasonable proportion of the outcomes, right? And we're kind of ignoring, the cases where the actual realization is going to fall out of those set bounds, right? So we're going to assume that someone who knows what they're doing gave us these set bounds, and we're going to believe them, right? And maybe that's based on models of physical processes, or maybe it's based on prior data. But somebody gave them to us, and we kind of take them on faith, right? And we're basing everything on those set bounds, right? But, I mean, real life really has more of a probabilistic uncertainty, right? So, I don't know, if I'm driving from Jerusalem to Tel Aviv, I can say it takes between 45 and 120 minutes, right? There are actually cases when it takes 5 hours. For example, if there was snow. Right? Once every 5 years there's snow, and everyone goes crazy. So what I really want is a distribution on how long it takes to drive from Tel Aviv to Jerusalem, right? And then I want to think about what is a good choice for my uncertainty sets, right? For my upper bound and lower bound that I can think about. And so instead of relying on someone telling me, okay, it's going to take between 45 and 120 minutes, I want to work directly with the probabilistic description of how long it takes, and I'm going to make my own decisions on what's reasonable and unreasonable durations. Okay, which outcomes I'm going to consider and which outcomes I'm going to ignore. And basically that's the idea of chance constraint or risk bounded, right? So I'm going to obtain my descriptions via the same models and data that the expert who would have given me the set bounds did. And I'm going to do mathematical programming, okay, to get these sets, these uncertainty sets. So with a probabilistic duration, right, it kind of looks like a contingent link, except it doesn't have an upper bound and lower bound. It just has a distribution on how long it's going to take, right, between x and y. Right, and then the end is again a contingent time point. And we also have the restriction that we had in STNUs, which I don't think I mentioned, that two probabilistic durations do not share an endpoint, right? Because that kind of doesn't make sense. You can't trust nature to make two things end at the exact same time point. Right, and so we're saying y minus x is distributed according to dxy, okay? All right, so PSTN, right, kind of looks like an STNU. It's got a set of executable time points, contingent time points, requirement links, like an STNU, and it's got probabilistic durations instead of uncontrollable durations, or possibly in addition to uncontrollable durations. And so we can take this Endor example and convert it to a PSTN, right? So we're going to say that the fleet hyperjump is going to take is going to be distributed normally around 600 with a variance of 3600, which translates to a standard deviation of an hour. Right? And the ground assault is going to take an average of 300 with a variance of 625, again using a Gaussian distribution. We like Gaussians, everyone does. Okay. So how can we schedule PSTNs, right? So with an STNU, right, we can ask whether it's strongly controllable, and that means, is there an assignment to executable time points that's consistent with every outcome of the uncontrollable durations, right? But for a PSTN, if we're going to ask if it's consistent for every outcome, we're going to be in a world of pain, right? Because a Gaussian is unbounded, right? So things can take infinitely long, and if we have a deadline, well, we can't do strong controllability, right? So we don't want to handle all the outcomes, right? What we want to do is we want to do a risk-bounded strong controllability, right? So, or a chance-constrained approach. And basically, we want to handle enough outcomes, right? So we want to find a schedule which is consistent with a probability of 1 minus delta, or delta, depending on the delta, if delta is the risk or the probability of success, right? So this is what we call chance-constrained probabilistic simple problem. Right, so we want to find a schedule which is consistent with outcomes with probability of at least delta. And that's right, kind of similar to going from A to B without crashing with a probability of at least delta, right? Or following a QSP without crashing with a probability of at least delta. And right, that basically means that I want to find a schedule which works for a guaranteed proportion of the outcomes, right? So I don't want to handle all of the outcomes. I just want to handle kind of the main probability mass of outcomes. Right. And the way we're going to solve this problem is through risk allocation, right? So we're going to, as Brian did before, right? We're going to use the risk as a resource to find manageable set bounds on my uncontrollable durations. Right, so the idea is this. Suppose I have a 10% risk budget, right? I want to succeed 90% of the time. That means I have a 10% risk budget that I can allocate. So I take this, right? So right, the constraint is that the probability of missing the deadline is less than 0.1. And I can do the same thing as before, which is the union bound or Boole's inequality, and I say that the probability of missing a deadline is less than or equal to the probability of the union of unexpected outcomes, right? So I have some expectation on how long thing is going to take, right? And let's say I know how to handle the cases that are within these expected outcomes, right? But if one of the unexpected outcomes happens, right, something takes too long or too short, then I might miss the deadline. And the union bound comes in here, right, where instead of looking at the union, I can sum over the probabilities of these unexpected outcomes. And again, I'm introducing some conservatism, right, but I'm making my problem manageable. So I take my 10% risk budget, and I can allocate that between different uncontrollable durations. And so, right, let's say this is duration 1, duration 2, duration 3, okay? And now when I'm looking at a specific duration, okay, I gave it some amount of risk, right? And I can allocate that. So I can say, right, this is, let's say I choose, this is my lower bound, this is my upper bound, right? And I can choose them. So what does it mean for something unexpected to happen? Well, if this takes less than the lower bound, so it's unexpectedly short, or more than the upper bound, which means it's unexpectedly long. Right? So these are my unexpected outcomes. And the probability mass of these unexpected outcomes, right, is here. So I can easily compute that from the CDF of the distribution, right, from the cumulative distribution function. So this is the approach. We're going to start with the chance-constrained probabilistic simple temporal problem. Then we're going to do risk allocation, right? So we're going to take our 10% budget, allocate that to the different durations, right? Choose the lower bound and upper bound for each. And that gives me an STNU, right? Because now I have a lower bound and upper bound on every uncontrollable duration. And for the STNU, I can do STNU controllability checking, and that's going to give me a schedule or execution policy, right? And so we're going to concentrate, as I said, on strong controllability today. So, right. So we know how to check strong controllability of an STNU, right? We're going to do the risk allocation and get an STNU, and then we're going to check if that STNU is strongly controllable. If the STNU that came out of the risk allocation is strongly controllable, then what I have is a schedule that works for at least the amount of chance I'm willing to take, right? Okay. So one way of doing that, right, is to formulate this as kind of a one-shot mathematical programming problem. So we want to prove that the STNU is strongly controllable by finding a strong schedule, right? Which is, right, I want to find two things now in the same optimization problem. I want to find execution times for the executable time points, and I want to find lower and upper bounds for my probabilistic durations, right? such that the probability chopped off by the bounds is less than the chance constraint, right? Basically, I'm not taking more risk than I'm allowed to. And the execution times are valid for the resulting ST and U. Okay? So I have two types of decision variables in this problem, right? The executable events, right, which is basically when I schedule them, right? So choose a numerical value for the events. And the lower and upper bounds, right? So these are also decision variables, right? So for each uncontrollable duration, I have a decision variable, which is what's the lower bound of this duration and what's the upper bound of this duration, okay? So if we're looking at this example, right, the indoor assault thing, so I have my executable time points, which are variables. I have, right, so these are start, fleet, hyper, jump, and ground assault, right? And then I have my lower and upper bounds, which are, right, the lower and upper bound on this duration and the lower and upper bound on this duration. Okay, so for this PSTN, I have 7 decision variables. Now, what are my constraints? So first of all, I have my risk allocation constraint, which says that the probability of something unexpected happening is less than delta. And, right, that translates into, so this is, again, conservative, right, but it means that the probability of violating the lower bound on D plus the probability of violating the upper bound on D is less than delta, right? So for all durations, right? So that's basically taking doing the union bound thing. Okay? So in this example, right, this is what it looks like. Suppose I have a 15% risk budget, then the probability of the fleet hyperjump taking less than the lower bound, right, plus the probability of the fleet hyperjump taking more than the upper bound, right, which is 1 minus the probability of taking less than that, right, because distribution, right, plus the probability of the ground assault taking less than the lower bound, plus the probability of the ground assault taking more than the upper bound, is all of this together is less than 15%. Now, of course, when you actually write down the CDF, if it's a Gaussian, right, it kind of looks horrible. But that's why we use a nonlinear solver, which can handle that. Okay. Now, the other constraints are basically the strong controllability constraints of the STNU. Okay? So for each requirement in the STNU, I perform the reduction that I showed you before when I explained how we do strong controllability checking. Okay? So if we have an edge going from X to Y, which is AB, right, a recurrent link, then that's case 1, and I just add Y minus X is between A and B. If I have something that looks like this is case 2, just drawn differently, then I add this, right, A minus the lower bound on D is less than Y minus X, which is less than B minus the upper bound on D. And then case 3, again, we saw this, and case 4, which looks horrible, but it's really the same idea. Okay. So, right, in this example, then, right, I encode my constraints. So this is going to take between 0 and 360. This is going to take between 0 and 180. This is going to take between 0 and infinity. This is going to take between 0 and 300. But I have to consider these, right, because this is between contingent. So it's kind of this horrible mess. And notice that the upper bound and lower bounds that I chose are here, right, because this is how the two constraints are related to each other. Okay? Right. So we have a nonlinear optimization problem, right? And we can solve it. We use SNOPT or IPOPT usually. And we can get a solution. And right, since it's kind of nonlinear and weird, we can get a schedule that looks like this, right? So we're going to start the ground assault at 151.3. We're going to assume that the fleet hyperjump takes between 498.3 to 701.7, and the ground assault is going to take between 253 to 347. Okay, so that just comes out of the solver, and this is a schedule which is going to work for at least 85% of the cases. Okay. So the one-shot approach, right? Yeah. No, because I have no idea how the solver works. It's something that we download and run. Bad, but yeah. No, I don't actually know, but I can introduce you to some people at the Technion who might. Right. So basically, right, the one-shot approach, we use cutoffs and execution times as decision variables. We take our chance constraint as a function of the cutoff variables and controllability constraints from STNU. And right, this is kind of the CRA approach for path planning. Now, before, right, Brian mentioned the iterative risk allocation approach for the path planning, right, where you kind of found the path and then you saw where you took the most risk, and you said, all right, I'm going to take more risk here and less risk over there, right, and kind of do that iteratively. So is there an iterative risk allocation equivalent to PSTNs? And what do you think, considering that we still have a half hour to go? Right. So there is one. It's called Rubato, and it's one of the only tools in our group that isn't named after Star Wars, because Andrew Wang plays piano really, really well, I'm told. I don't actually understand, but yeah. So the idea is this, right? When we're doing the STNU controllability, right, we want to discover conflicts here and feed them back to the risk allocation, okay? So what we're going to do is we're going to use risk allocation to generate a candidate STNU, right, which is going to include maybe only some of the constraint instead of encoding all of the constraints beforehand. And then we're going to check controllability of that STNU. And if it works, then great, we're happy we found a schedule. If it doesn't, then we extract conflicts, right, which are linear constraints, for a new round of risk allocation, which now has an additional constraint to consider. So the idea is this, right? When we're looking at an STNU, there is a lot of redundancy in the constraints because some constraints imply other constraints, right? And maybe some don't. So the nonlinear solver is expensive, right? And so we're trying to make its life as easy as possible by giving it as few constraints as possible, right? So the idea is that we start with very, very few constraints, and then we check whether the solution that it gives us is feasible. If it's not, then we add more constraints as needed. And what that does is allows us to use specialized algorithms for STNU controllability checking, rather than having our solver do that for us. So, right, this is how it works. First, we just do the risk allocation. Okay, so we call the nonlinear solver, and we say, hey, give us a risk allocation that satisfies the chance constraint. Doesn't consider any temporal constraints whatsoever, right, at this point. So if we're doing the Endor example, right, with the 15% chance constraint, then it's going to give us this allocation, right? So this is going to be between 255.5 and 344.5, and it's going to be between 493.2 and 706.8. Just numbers that the solver gave us, right? And again, the solver now doesn't know that there are any temporal constraints, and it doesn't care, okay? And now what we can do is we can check whether this STNU is strongly controllable, okay? And there are efficient algorithms for doing this because people have been doing STNU strong controllability for 16 years now, right? And since we know the structure of the problem, right, which the solver doesn't, then we can actually use those more efficient algorithms. So we can do those triangular reductions I mentioned, right? And we detect a negative cycle, which means that I have a conflict, right? So I have this negative cycle here, right, minus 2.6. Okay. So what I'm going to do now is I'm going to extract a conflict from that negative cycle, okay? So I need to know, right, that this negative cycle here came from L fleet, U fleet, L ground, U ground, and this, okay? And so I'm going to encode the additional temporal constraint that says U ground minus L ground plus U fleet minus L fleet minus 300, right? Kind of this thing is greater than 0, which means basically don't give me this negative cycle ever again, right? And then I'm going to call the nonlinear solver with this additional constraint, okay? Right. I'm basically telling the solver, give the ground assault more time. And for some reason, it keeps looping. So I don't know why it does that. But yeah. Okay, so I'm going to call my nonlinear solver with these two constraints now. Okay? And actually, this is enough. Right? This is going to work. So you don't actually need all of the constraints. Right? You only need, depending on the problem, of course, but sometimes you only need 1 or 2 temporal constraints to give you a valid, strong schedule. Okay, so this is actually much faster than I thought it would be. Right, so the idea with the iterative approach, right, is that we generate STNUs via risk allocation, and then we use specialized algorithms to check STNU controllability, right? And if there are conflicts, we add them and kind of iterate, right? So this is much more efficient because we use specialized algorithms for the controllability checking. The risk allocation has a lot less constraints to consider. One thing that it also gives us is that there's no explicit schedule for execution, right? So kind of we have the schedule from the STNU. But the solver, the risk allocation, doesn't give us the schedule. So, so in fact, if you're trying to optimize something, right, then if you have an optimization objective, right, when you're doing the CRA approach, the one-shot thing, then you can also give your optimization objective as the optimization function. With this approach, that's trickier, right, because when you're doing the schedule, you don't have the full power of the nonlinear solver, so you can't necessarily optimize. So this is more suited maybe for feasibility checking. So maybe we want to run algorithms for execution once we found a feasible risk allocation. Okay. So, right, this is basically the same conclusion that Brian had. We want to maximize utility under bounded risk because it makes sense, and risk allocation can help us do that.